Hello there, thank you for joining me again today. Welcome to the wonderful world of RF electronics engineering. On the bench for repair today is a Kalmus wideband amplifier. This is a 10 watt model, does a maximum of 10 watts output with 0 dBm input in the range of 1 megahertz to 1 gigahertz, so it's a 1 gigahertz bandwidth RF amplifier, which makes it rather unique because most RF amplifiers that we come across these days are narrow band and can produce lots of RF power, but they're only suitable at one particular narrow band of frequencies, whereas this is a very wide band RF amplifier. These were designed by Kalmus to be sold to the defence industry for testing things like radar systems, calibration of signal sources, or to provide a drive source for repair of klystrons, travelling wave tubes, RF power amplifiers, be it bipolar or FET devices, also testing all kinds of RF equipment. Also they're used by manufacturers as well in labs to set up and calibrate equipment that's being manufactured by them. Also test equipment labs use them for calibrating RF power meters in radio communications, test instruments, radio astronomers use them as well to drive certain sources and things, or to be a reference source for a particular measurement. All kinds of different scenarios, but this is mainly made for the defence sector in that case, and this is where this has come from. This is ex-Royal Air Force, is this amplifier. Now, I bought this from an auction believing it to work. Paid rather a lot of money for it, more than perhaps I would have done under normal circumstances, but it was in an auction. I was bidding against other people. Unfortunately, in my case, this is sort of a Freddy Cougar of RF amplifiers, because when we got it, as you'll see in the upcoming video, it didn't produce any output power really, just a few hundred milliwatts at full gain, and it was disappointing because I paid, as I say, a lot of money for it. And I've had to pay about £30 in parts to fix it, because it's now up and running, it's working properly. But it was a nightmare to fix. It truly is the Freddy Cougar of RF amplifiers, is this. You'll see when we get the lid off in the upcoming video just how difficult to repair in regards of access it is. There are 4 RF amplifiers inside this, plus a 5th, which is a preamplifier, and 2 RF combiners, all of which had faults on them, and you'll see in the video that we go right way through fault finding to component level. Bearing in mind I've no service information for this amplifier, I've no setup instructions or anything like that. And anyway, in conjunction with this repair, we use the spectrum analyzer as well, and we sweep the amplifiers, each one of them, on the spectrum analyzer using a combination of RF attenuators and drive source from the track gen on this. We use that really to align each amplifier's bias as well as its to calibrate its RF performance right the way across its frequency range at a linear level. We use a SIG gen as well independently to do sweeps, and also provide drive sources for the amplifier on set frequencies, so that we can test each amplifier individually, externally of its own internal and external combiner, so that we can make measurements of each individual RF amplifier. It was definitely a nightmare to strip down this amplifier. Once you get it apart, the way it's built and constructed, they've gone really to town on screws and fastening it together. Very difficult to access some of the modules inside. Major strip down job just to get to 2 other modules out of the 4. The RF combiner had a weird problem, which you'll see. Not something that I'd expect to see in a combiner, but there again, anything can happen on this bench. And really, this is quite a very nasty amplifier to repair, considering what it does. I mean, for its size and weight, a normal narrowband amplifier of this size will produce many thousands of watts RF power, but as I say, this is a unique amplifier in the sense that it's designed for the meteorology industry, the laboratory environment, that kind of thing. So it's a very high precision linear amplifier which needs a continuous gain across from 1 megahertz to 1 gigahertz. So it's very unusual to get amplifiers like this, and normally these would be very, very expensive to buy new off a shelf. But I can't help but feeling that I've been bent over the desk on this one, because the RF amplifier itself came to me meant to be working, and when I got it, it wasn't. And this is the thing when you buy things from auctions and things, you've got to be so careful. But unless you can see it working before you make a bid, then really you're taking a gamble. And unfortunately, I've lost out on this one. Maybe not, depends how you look at it, but if I were to sell this again, I wouldn't get my money back for it, I don't think. So I've made the decision to keep it. Anyway, I'm sure you'll enjoy the upcoming video. It's a very interesting time. We go through it quite quickly, methodically. We order the parts from Mouser as well, which seem to supply the RF resistors that we'll need in this particular case, and unique problems and things that we'll go through with it, which you'll see. But it's a very challenging repair indeed on this one, simply because of the way it's constructed, and the amount of work required to get to things is unbelievable. But anyway, you'll see that in the video. So sit back, enjoy, and look forward to seeing you in the upcoming part of the video. Okay, so whip the lid off. Now we've got the screws out, and it's full of RF gubbins. The lid is very well made. It's proper thick metal, it's not thin tinny stuff. So it's well made, is that. Let's say get what you pay for. But this is what's in the amplifier. So if I just turn it up a little bit, and then we can have a look at it inside. Okay, so we've obviously got on the far left hand side here the mains filter. It's quite important for EMC compatibility and to prevent RF from escaping down the mains cord, that there's an EMC RFI filter fitted, which tends to be standard in a lot of test gear these days. It's got inductive capacitive elements in it, reefer caps, etc., and series inductors that choke off any unwanted signals or whatever from leaving, or likewise coming in from the mains, causing interference. We've got at the top here an exhaust port which allows air, which you'll see in a moment with the heat sinks, that these four modules are bolted to. 1, 2, 3, 4 there, bolted to a large heat sink, and then blowing through the middle of that heat sink from the fins on this side to the right hand side here, it sucks air in and then blows it out the back, or the other way with a fan here. So these are the 4 amplifier modules, which seems quite a significant amount considering it only does 10 watts, but that's the way they've designed it. Okay, down here at the bottom is a high power combiner divider, and again that's rated to, I think it says there 19 watts, it says 19W, frequency 1 to 1000 megahertz, and company name written on it. We've got a mini circuits power combiner here, which is obviously the low power combiner. This is the input, so we've obviously got the coming in on the left here, down here we've got the input RF coaxial cable, which is this. So that leads to the front socket down there, and basically that comes up here on this side, goes into this SMA on this module. This module's got a supply connection there, a negative and a positive connection on a feed through capacitor, which you might be able to see down there if I just zoom in, and there we are, look. So that's what we've got. We've got positive and negative supply to this module, gain control probably there. And so what that does is that obviously amplifies the incoming RF signal from the input socket on the input there, and then amplifies the output. The coaxial cable from that then goes into the top port of this which is the S port, signal input port to this mini circuits power divider. And then we have then a separate feed coming off, one there, another feed here which goes under this. So these two here, these two coaxial cables going to these two modules there on these connections, those two. And then likewise, similarly on the right hand side here, we've got another two there which then go off all the way around to these two modules at the top as well, go to these two. So that's where we've got the one single input at the top of the module and then 4 outputs, hence, you know, 4 modules. The outputs of those 4 modules then connect into this, as we can see with the coaxial cables that go around, and likewise this coaxial cable goes round there to this output. So we have 2 amplifiers in, 2 amplifiers in, and then we'll have an output here which is on the right hand side, which is a combined RF amplified output. Hence the reason why there's a difference in physical size between this mini circuits power divider, which is only low power, in the order of maybe a watt maximum that could deal with, and then we've got a high powered version of that which is rated to 19 watts maximum, which is here. So if this gives a 10 watts output, for example, then this power divider will be working at roughly 50% its maximum, so that keeps it underrated so that it's not flogging its guts out. Obviously everything's bolted down to a large metal plane that's part of the heat sink, and all bolted down to prevent it from overheating. The output signal that's fed out of here on this combiner output then goes in a direct coaxial cable down to the top end there where the N-type socket is, just here. So the type N output is connected there, so it goes straight out. Now what we've got underneath this entire unit here, this section, is a switch mode power supply. And if I just turn it over onto its side a little bit, you can see, I think just down there, just hiding in this gap down here, there's some connections down there which I believe are the output, and then the input, which is this obviously live neutral cable, brown and blue, which goes over to the switch at the front and then comes back, then connects into the switch mode power supply down there, and the terminal block on this side as well as a input output element on it down there. So again, you know, it's a high current low voltage power supply. I think these Kalmus amplifier modules, like the other one that I've got, tend to run off about 24 volts DC. So, you know, obviously it's not a high voltage system, but certainly not 12 volts either. Anyway, we've got some more, got a big chunky reservoir capacitor across the supply rail there for something. Looks like this is the fan supply and maybe some supplies for other things like this amplifier here. So that's what that's for. Looks like as if we've got some kind of a resistor to discharge it or whatever. There's another capacitor down there and a connector going off. Very well made indeed, well put together. Everything's nicely fastened down and clipped in place, and all the SMAs have all got this good quality aerospace grade coaxial cable. It's very low loss, very good performance right the way across its frequency range. And then of course at the front here, which you can probably see down there, we've got the modules bolted onto the heatsink. So that obviously gives us that good thermal conductivity from these RF amplifier modules that are bolted on the side here. And then they obviously give a nice airflow through the middle of this exhaust chamber, which, as you can see, goes right the way to the back. And that's about it, really. There's not much in it other than that. I mean, you just got the usual supplies down here, using these feed-through capacitors onto these RF modules, and then obviously then, you know, it goes out off onto the amplifiers inside, and then they're obviously bolted to that that heatsink as well. So quite an interesting little device. I think we'll power it up and see what we get out of it. I mean, this module here, what's this here? High power combiner. Is that Whirlertone Incorporated, Brewster, New York? Looks like it. Can't say I've come across them before, but they've probably been around for a long time making things for the defence sector. But they put all the details on there: frequency, power rating. Does that say 15 watts or 19 watts? I read it as 19, but it isn't, is it? It's, I don't know, I think it's 15 watts, I think. Yeah, but it said 19 when I read it upside down. It's actually 15 watts. So when it's running at 10 watts maximum, then it's got a bit of 5 watt headroom in it. As you can see as well, they've got these anti-tamper labels as well for warranty void if removed. So they're being very careful at making sure that nobody goes into it that's unauthorised, starts faffing about with it or going in for doing any repair work. It's the same with all the modules that are in it, like this one. That's got the sticker there as well. Warranty void if removed label. So anti-tamper labels throughout. It's got a nice pair of handles on the front as well, but again, these have got labels on them too as well. So once you break those, that's it. It invalidates its, you know, its integrity. What you've got to be careful of as well when you're stripping these kind of amplifiers down, doing any repairs, is not disturbing where they put RF absorptive like cushioning. They'll often put certain things in there which they'll do under test when they produce the amplifier, where if there's any wanted RF spurious or harmonics, they'll put some RF absorbers in different places, and if you disturb those or you disturb anything around that area, then it can throw all that amplifier out of calibration, and it might start doing things at certain frequencies it's not meant to do. So you've got to be really careful when you're working on these, that you know, you do everything precision. You replace the components with the exact same components that were there to start with. So if you're replacing transistors or capacitors, things like that, you don't substitute different ones, because it all has an impact on its overall specification. So I'll just show you another Kalmus amplifier which I've had. It came in a box similar to this, but the power supply had blown up in it, and it had other things missing as well that somebody had robbed parts out of, but I saved the main amplifier thing and I still use that to this day. So I'll just show you that now as well. Okay, so I just wanted to show the output performance on this amplifier. It looks like as if we've got a fault on this amplifier, and it's the reason why it was ended up in my hands. Now what we're doing, according to the front of the instrument, we've got a reading here where it says 0 dBm. So really I'm expecting 10 watts output from the RF output port here at that sort of level input. And with that wound, the control wound to maximum, all we're getting is a very small amount of output power. So this meter here, just to keep things basic, I've decided to use a Raycall absorption wave meter, watt meter. We're on the 10 watt scale, and a full deflection on this will be 10 watts, so it's on the upper scale here. The 30 watt scale is when the switch is in that bottom position, but in the top position, reading the top scale. And as we can see, with 0 dBm input, it's doing about 500 milliwatts, because 1 watt is just there. Now, if I increase the output on the signal generator, we've got the IFR signal generator set to 100 megahertz at 0 dBm. Now, I've tried different frequencies and the power just varies a little bit, only marginally. But if I drive the amplifier into compression, then by increasing the output level up to 10 and plus 20 dBm, then the actual power starts to go down. So if I just show that now, I just increase the signal input to the amplifier, or the output from the SIGGEN, to just demonstrate that. So if I chose 10 dBm, you can see the gain of the amplifier is reduced. If I choose 20 dBm, then it's gone up a little bit as well. So that's with 20 dBm input. But it's not producing 10 watts output. But at 0 dBm, it's producing just under half a watt. So I think there's some weird biasing conditions going on here with the amplifier, but it's always worth having a look. Now, what I've done, just before going into this section of the video, I'll just turn this round again so we can see inside. What I've done is, obviously in this particular format, we've got the input combiner, which is this mini circuits device down here. That's where the RF signal comes in, and then it's split out to all the 4 different amplifiers. What happens is, before it gets to these amplifiers, it goes through a preamplifier, which is this here. So the input signal fed from the N-type socket on the front here goes straight to the input of this preamp. The output of this preamp, which is down here, this connector, goes straight in then to the input of the mini circuits combiner. So the supply voltages to these amplifiers are fed in on feed-through capacitors down here, which we're going to measure shortly. But just before getting to this section of the video, what I've done is I have disconnected each amplifier's input and output connectors, and I've then measured the amplifier performance separately, directly, by connecting an RF input from the purple cable, which is feeding a signal in here from the signal generator, straight into the input of the amplifier, and then the output of the amplifier we then fed through an N-type to SMA adapter straight to the recall power meter down there, you see. So I can measure each individual amplifier separately. Now, of all 4 amplifiers that I've tested, this amplifier produces nothing, no matter what the input level is. That one produces nothing. This amplifier here produces a little bit of something, a few hundred milliwatts at most, and this amplifier produces about 1 watt. So this measurement that we're seeing here on this recall absorption wave meter, this level here, is actually from that one amplifier round the back. So in order to get about 10 watts out, these have to do 2.5 watts each roughly in order to produce a total of 10 watts. They'll do more than that obviously, but that's just a spec rated for this amplifier's 10 watts. Anyway, so looking at it inside, we've got what appears to be just a straight supply really that connects in on this feed through capacitor here. Then we've got the pots for altering the biasing as well, and the RFCs as usual, the amplifier transistors themselves, which we'll have a look at in more detail. But what these are, these elements here, particularly these two, these are attenuator pads, and they're the type that would normally bolt down to a heatsink. But what they've done, they've soldered them onto the gate and the drain source on the FET, so that basically a feedback element to give a feedback between one side and the other. And as you can see, there's a capacitor, if you zoom in a bit closer, soldered from the leg of the attenuator to the what is a signal output. So the DC that's on the transistor can't go back to the base or the gate or the FET and bias it fully on. So it's AC conditions are allowed through, but DC conditions are stopped. And it's the same here. So that's what these are for. Now, where a fault could have occurred on these, because one of the amplifiers, which is one of these at the back, if you overdrive it with about plus 20 dBm, it then produces a couple of watts of output power. So there's a couple of things that may have gone wrong, and we'll just switch this off. So there's a couple of things that could have gone wrong. You might be able to see down here there's a voltage regulator IC, and this voltage regulator IC provides a step down voltage from the plus 27 volts that's fed here to a much lower voltage that then supplies the biasing networks, which are set by these potentiometers. So it could be that the biasing just needs setting up on them. It could be that this device has failed as well in a couple of the amplifiers with the current that it's having to provide. So we'll have to measure the output voltage on that. These potentiometers may need setting to provide the right bias conditions for these transistors. As I say, with this amplifier at 0 dBm input, it wasn't producing anything. But we'll just do another test now where we increase the input in order to see what we can achieve on the output. And that would prove that it was biasing conditions. If the RF transistors have stuffed, then they'll not produce any output power at any input level, no matter what. So yeah, that seems like the most easy and likely cause will be biasing plus this device perhaps failed. This has got a trimmer cap as well, which I'm not sure how that's set up on this, whether it's aligned at 500 megahertz, which is halfway across its entire frequency range. I'm not sure, so I'm going to avoid trying to touch that. But certainly I can adjust the biasing conditions. I'm going to have a look online as well, see if I can find a manual for this, which I don't think will be available. Well, some details about the setup procedure on these. But if I could get an input level measured, I suppose I could try and input 0 dBm into this amplifier, measure the output level in dBm to find out what gain this amplifier provides, and then whatever that level is, I'll then need to feed equivalent into here, into the input, so that we're driving this amplifier with the correct level, representing a 0 dBm input from the front that's amplified. Might amplify it to plus 33 dBm or something, and that enters this. So I might need to input plus 33 dBm to then calibrate the biasing on this and the conditions in this amplifier, or perform repairs so that this gives 2.5 watts output, and do that with the other three. And that way then when we calibrate the whole 4 of them, one of them's working, as I say, then that would mean that we could potentially get 10 watts output then, because obviously we're producing 2.5 to 3 watts per amplifier. So I'd have to look at the biasing conditions and things. It might be a case of looking at the working one on the other side and measuring the bias volts on that, or what current it's taking. The gain control on these isn't by changing the voltage up and down, the supply voltage to this amplifier from the front potentiometer via a series pass regulator. How it's actually achieved is the voltage to the preamp here is adjusted up and down, and this electrolytic capacitor is across the supply there. So the control voltage to this amplifier is changed depending on what the rotary control on the front set to, and that then controls the gain, the output gain. So I think what we'll do, we'll just feed an input signal into this device higher than 0 dBm to see what output it produces, if anything. and then take it from there back soon. Okay, we've connected the wave meter now up to the output, and then the input goes straight to the signal generator. So what I'm going to do now, I'm just going to turn the supply on. I'm just going to measure down here on this feed through just to make sure we've got supply voltage. Always check that first. No point looking at countless possibilities unless you've checked the supply. Because obviously nothing's going to work without that. So I'll just put that there, and then we'll go on to the meter, switch it on. So we're currently not getting any power anyway on the meter. 0 dBm fed in, no output power. So that's a shame. But anyway, we'll have a look on the voltmeter now and see what we've got. Now if I have a look on the flute meter over there, we've got 27 volts. Interesting. So what I'm going to do now as well, first of all I'm just going to increase the level on there to something like plus 20 dBm to see whether we've got any output power on here. So let's do that now. So I'll put 10 dBm to start with, and there's a little bit of power showing, look, just a smidgen. So I'll increase it to plus 20 dBm now. 20 dBm. And we've got some juice coming out, 1 watt. Let's have a look, see if I can get it to 30 dBm. I think it won't go that high on this particular 30 dBm. 25 dBm. It'll produce 25 dBm. So we're getting 2 watts at plus 25 dBm coming in there. So that's pretty good. That tells me that those transistors are not stuffed. So I think it might have something to do with the biasing conditions. So because I don't know what the amplifier is meant to be driven with when the gain's at full control, up to maximum, the RF gain, I'll now need to measure the amplifier, the preamp, to see what the output level is on it first, in order to ascertain what drive level should be coming in here. And then, knowing that information, I can then look at the biasing conditions to check to see whether the biasing is set correctly to produce the output level on the output here. Otherwise I'll be clutching at the straws. Right, so I'll reduce that back down to 0 dBm again. And while I'm here, I may as well have a look at the biasing conditions on those transistors. So I'll just have a look at that now, see what we've got. So, right. Let's have a look. So, on this one, let's have a look. Just waiting for the meter to measure. Well, that's interesting. I'll move this meter over so we can see it. Rather right. Get those cables out of the way. So. You just see whether I can get this magnifier on it. Right, so going on to the gate on this FET, we've got a voltage there of plus just under 6 volts, 5.989 volts DC on the preamp. Let's have a look on this one. .9 volts, and then this one that's strange, 25.66 volts there. That's strange. I wouldn't be expecting that to be there. 25 volts. Seems a bit high. But there again, who am I? 25 volts there, you see. And of course then on the output, on the source, I think there we're looking at plus 26, so that does seem quite high, that's present on there. Again, there's another 50 ohm feedback thing, but I wouldn't have expected such a high voltage there. Got a potential divider resistor down there that potentially that could have gone open circuit. To get 25 volts on the gate is a little bit high. Plus 22 volts there before it gets to the, obviously what's been, how's that getting 25 volts then? If that's 22, let's just remove the RF input just in case that's having an effect. Could be that the meter's picking up a bit of RF that's there. You'll only need 100 milliwatts if that, and it'll disturb the meter. So let's just unplug the RF. So we've got 22.41 volts there, and then here, and get it when it measures it, 25 volts. So there's something coming back from what would be the supply developed across this choke. It's getting back. Now there is a capacitor here that's meant to stop that from happening. So how that's getting back, I don't know. There might be something leaking. Might be something leaky going off. Because there's a capacitor just here that solders down. If I can just zoom in on that. There's a capacitor there. So quite how it's getting that high voltage, I'm not sure. But there's a, I can probably just see it there. I'll get the camera just to focus in a bit better on it. You can just see that there's a capacitor stood on its end just there. So, you know, obviously we're getting about 26, 27 volts here. We're getting 22 volts roughly before this resistor. It gets to there as a potential divider. But we're getting more volts here, there, than we are there. So something's feeding back, I think. I could unsolder this to confirm if this capacitor's leaking. But there's no other components feeding a supply onto here. So that seems a bit strange. I might to open up the other amplifier next to it now and see whether that's suffering with the same problem. It's a bit weird, is that? So the plot thickens. Okay, so we've got the second amplifier apart now, which is over to the left side of it. So I'm just going to measure the biasing conditions again on this one. So I'll just have a look at that. Let's go on to onto here. See what we're getting. 5.991 again. Now that's different. 4.792. And we all know that there seemed to have a higher voltage than prior to the potential divider. 24.62 volts, whereas there it's 21. I'd love to know where that gate is getting the extra voltage from, unless it's leaking through from the drainer source connection back. So that potentially could be what's happening there. So it could be normal, but I don't know. .6 volts. So this will be supplying current rather than voltage, but it's just interesting, that's all. Now this voltage regulator I see here outputs on this pin there. I think it's on this pin there. Yeah, it's a 12 volt voltage regulator, outputs 11.8 volts DC onto the output of that. So that works. Now I've just wondered if I could go out a second, just move back over to this amplifier. And we can have a look at that as well. So let's have a look at this component. Just measure the output of that voltage regulator just to see whether that's the same, 11.94. So this could be down to biasing as well, or it could be down to a few things really, but we're going to definitely have to look at driving both these amplifiers with the right level for the based on what the preamp gives, and then try and adjust the biasing maybe to give the right output. So on the gate on this transistor we've got 25.7 there. What have we got before on that resistor leg? Yeah, 22. So it's interesting, there is some leakage through then back to the gate. So that's going to be interesting. Right, I think the next thing I need to do now is to get the preamp, which is down there, that module, measure that with 0 dBm in, see what level comes out, and that'll give me an idea then as to how much power needs to be driven into this. We'll see what that reveals, and then we can go from there. Okay, so what I've done just before getting to this stage of the video, the preamp module that's down here, I've connected to the output an SMA to N-type adapter, which is this. That's on the output. We've fed in on the input here 0 dBm as per the input level that's meant to be fed in. Turn this control up to maximum, and then on the absorption wave meter I just needed to check before we use the Marconi sensor with the Marconi power meter. I wanted to make sure that that output did not exceed the 100 MHz test frequency we're using more than 3 watts. Reason being is because this is only rated, you see, to 3 watts maximum, even though it's got the heatsink there. That can only tolerate up to 3 watts, so I didn't want to risk burning that out because that's a very expensive sensor. So what I've done, I've just needed to verify that, because obviously if the amplifier were ever to produce say 3 watts or above, then it could cause damage to that that sensor. So now what we need to do, we've introduced this instrument which is going to show us the gain, the overall gain of that preamplifier in dBs. But we're going to attach this to the output of the preamp. We know the input to the preamp 0 dBm because we set that up on the SIGGEN. We've got this sensor now, we just need to calibrate this sensor with this instrument. Excuse me. So what we'll do, we'll just connect this up now to the power reference port on the Marconi RF power meter, and what we'll do, we'll make sure that's nice and snug and press auto cal. So now it's putting out a 0 dBm signal into that sensor, and it's going to calibrate the sensor to 0 dBm precisely on there. When that's done, then we're ready to make our measurement. So we'll just wait that to happen because it's just going through that process. So I'm looking with this test then to see what the dB gain is of the preamp, because I don't quite know at this stage whether the preamp's outputting enough drive or whether it's at the correct level. So I just need to have a look at how much gain there is across that amplifier and take it from there. I've had a look online as well for this Kalmus amplifier to see whether, you know, I can get the manual for it, and I can't. I've no idea where the service manuals are, schematic diagrams. So we'll just check that cal now by reapplying the calibrated 0 dBm output power to this sensor. As we can see, it's reading there dB 0 dB, so that's spot on really. We're ready to make our measurement now. So I'll just remove this sensor and then we'll connect it to the output of the amplifier, and we'll start at the minimum level first and then work us way up. So what we'll do now, we will just wind this level right way down to minimum. I'll just go on to this amplifier output with the sensor, and that way then that at least it's connected nice and snug. All the connections are tight and everything. The sensor's there, look, on the output. We've got 0 dBm on the signal generator, and now we're ready to see what gain, if anything, the amplifier has. Now it settles around about minus 12 dBs, and that's because of the way that the sensor sensitivity is, because it's got that attenuator on it. So we're ready to, there's nothing connected or floating around that can short. We're okay with that. Ready now to turn this on. We're already inputting a 0 dBm signal in here, so now I'm going to start to adjust this gain control, and then we'll see then just how much output power there is, and we can read that in dB as well as power in watts in a moment as well. So I'll just increase it. Right, so that's maximum level there. So it's a 20 dB gain amplifier, which is about right, I'd say, for that 20 dBs. If it was really low, I'd know that there's a fault in that preamp stage, but they normally are at probably 10, 15, 20 dBs roughly, perhaps 30 dBs at a push gain on them, but that's a nice sort of round figure calibrated 0 dBm with 20 dBs output on it, 20 dBm's output. Now if we go to units on here, we can select, obviously there's dBm there, and then milliwatts, 106 milliwatts. So in terms of RF power, 0 dBm is equivalent to 1 milliwatts RF power into 50 ohms coming in here, and we're getting 106 milliwatts coming out, so that's a considerable gain. So if I reduce the gain control now on the amplifier, it's got quite a smooth control. Then we're going down in the ranges, 0 milliwatt. You can see the meters auto ranging on the left. So I'm happy with that. I can see that that's got a 20 dBm gain, dB gain on there, so I'm happy with that. We're putting 0 dBm in and getting 20 dBm out. So I'm confident now that it's the individual amplifiers that we now need to look at, perhaps with the biasing, perhaps something else, but at least that's where we are. You've always got to be careful though with amplifiers, particularly if you're using a sweep generator and you're sweeping an amplifier's frequency in order to find its performance characteristics. Some amplifiers can have very little gain at certain frequencies, and then they can just take off and the RF power goes straight up through the roof to stupid power, and then it comes back down again. And the trouble is, if you're using a sweep gen with a sensor like this, when it gets to that sweet spot and it takes off the amplifier, if it exceeds the rating of that sensor, then you've just stuffed a sensor which can cost many thousands of pounds. So you've always got to be really careful when you're doing sweep measurements of amplifiers. We're not doing that in this stage. We're using just a single spot frequency at 100 megahertz. But if we had a sweep gen on, then we could definitely damage that sensor if it was on the output of the RF power amplifier, if the amplifier had a non-linear response. So you've always got to be really careful. I always recommend, before using sensors like that, use a proper RF power meter, you know, a bird through line, RF meter, a radio test set that's got the power meter function built in, so that then you can get the correct assumption before you connect that sensor, because if you plug that sensor in, the power's too much, as I say, it'll blow the sensor. So it's always better to use an RF power meter with a high handling capacity in RF power in watts, so that at least you know beforehand, when you do use the scaler or the RF power sensors for the Marconi microwave test set or the individual power meters, that you're not going to risk damaging them, because once you do that, then yeah, it's definitely a face slapping moment, you know. Very, very depressing when you break one of those sensors. So we'll advance on now to the power amplifiers themselves and see what we can do about the biasing. Okay, so the aim now is for us to isolate the power supply that's within the RF power amplifier. So we've done that with that, disconnected these two connectors. So that allows us now to independently power these amplifiers, and then feed an RF signal in and then see what comes out. Now we know that the preamplifier with a 0 dBm input provides plus 20 dBms output. So I'm going to be feeding in here plus 20 dBms from our signal generator. We're now going to be providing from this Siglent power supply 26 volt supply to the RF module. We've set a current limit to 3.2 amps. So if everything goes wrong with the biasing, then maximum it can draw is 3.2 amps, whereas the power supply that's on this probably can supply 20-30 amps. So, you know, it won't cause any damage then, or as much damage. I'm aiming to get around about 2 to 3 watts output from this amplifier, no more. So I think we'll have a tinker now with the biasing on this amplifier stage to see what RF output power we can get. We've got the negative lead of the power supply connected to the chassis of the module, and then obviously the positive supplied to the feed-through capacitor on this side. So that should sort that out. So what I'll do now, I'll enable the output on the power supply on channel 2. So now we've got that. So we've got a 2 amp current draw already on that. So I'm interested in that quiescent current, you see, at 2 amps. And we're not really at 0 dBm. I'll just change the signal generator to 20 dBm. And so we're getting some RF power, something anyway, and we're drawing 2.15 amps at 26 volts DC, and we're getting 1 watt output. So I'm just going to have a tinker now with those potentiometers to see whether we can get that up. Really it should be 2.5 watts per amplifier to get 10 watts out, because there's obviously 4 amplifiers, so that's what we're going to have to look at. But yes, we'll have a tinker, see what we can do. It'll be interesting. Let's see if I can find my trimming tools. I had a box of them somewhere. You can never find them when you need them. Around here somewhere. I'll just find those and then I'll come back. Okay, we're back with the trimmer. So if we enable this to on, and we've got just under 1 watt there. Let's just have a tinker with these biases, just to see what we can get. So that's going up a bit. Not much difference there. Not moving the current much on the power supply. I know you can't see the power supply at the moment, but I can see it. It's 2.26, 2.27 amps. It's not really giving us much. So is it the final amplifier output then? No. Well, the output one there isn't making any difference at all. So it could be the output amps are stuffed on it. And that could explain why we're getting voltages on the gate, because the actual the source is leaking voltage through the internal structure of the transistor onto the gate, because that biasing pot's not having a blind bit of difference at all. Not a blind bit of difference. So it's drawing 2.45 amps, 2.5, 2.7 amps there, and then that's saturated it. The peak's about there actually, which is 2.32 amps with that bias. This bias here, we're getting it up, but it starts to 2.45 amps, and then it's drawing 2.6, 2.7, it's falling off amps. So its sweet spot is around about, I'd say there, 2.45 amps. So those two look like they're working okay. This one looks like it's not working. So we'll try this amplifier next now on this side to see what happens with that. But this biasing pot there for this power output transistor is having no effect. And with there being a higher voltage on the gate than there is before the potentiometer, it seems to me like as if this transistor's gone. So whether we can get a replacement transistor for this is another thing, but might have to look at that. Anyway, we'll have a look, see what we can do with it. But it is giving some power output of 1 watt. Whether it's not failed completely, it's just gone leaky or something, I don't know. But seems a bit strange. In actual fact, the plus 20 dBm coming in here will not be plus 20 dBm, because the little splitter will have 3 dB ports on it. So basically, if you put 20 dBm in, you'll get minus 3 dBs of that coming out in each port. So it'll be about 18 dBm coming in there. So if I lower that now to 18 dBm, and it's brought it down to just a few hundred milliwatts as that amplifier. So yeah, it's warm, but as far as the RF transistor goes, it's I don't think this final amplifier is working. We should be getting, you know, a good 2-3 watts coming out of that already. This needle should be up here on the scale, so you know, around about there, 3 watts mark. So, and it isn't doing that. I'm going to see whether the biasing on this now is different. see whether we can get this one working, and whether this has got the same problem. Back with you soon. Actually, I've just noticed something which may lead us to what the fault is, rather than it being the transistors. And I don't know why I've missed this. I'll try and show you, zoom in here, it should be easy to see, but see if I can get some light there. You might notice that on the transistors, let's have a look here, see if I can straighten this camera up a bit. If I zoom in, you can notice on the let's have a look. On these transistors there's an attenuator resistor which is soldered across the gate and drainer source or whatever to give RF feedback, and there's a capacitor which then obviously is there to isolate DC from coupling back to the gate but allow the RF to pass through. And these are little RF attenuators. If you notice down here, there's a piece of what looks to be a little island thing, which is one of these lugs. It's actually one of these back plates there, and it's dropped off this attenuator here on the final output. So it's obviously got way hot and dropped off, and that's what this is down here. So, and that's happened on both amplifiers. So it's happened on this one as well. You can just see it there, look. There it is. So they've been flapping around in the breeze, as Dave Jones from the EV blog would say. But you can see quite clearly that they have, this has detached itself as that. Matter of fact, it's just dropped off altogether. So that's that. So that's a very strange thing. It's just dropped off altogether. So it may be that the transistors are okay, but they're just not getting the feedback, obviously. So if I can find a pad that's the correct rating for these transistors of its dB attenuation, I might be able to repair it by putting in a pad in this section in order to restore that feedback arrangement. But it's obviously got way hot and then popped. So this is the resistor here. Let me see whether I can, I don't know if it's got a dB attenuation written on it or something. So we can have a look at that, can't we, through this magnifier, I think. Let's have a look. Maybe possible to see that. I'm wondering if we can see it through this. Looks like it's not got anything written on it, I don't think. Just have a look, hold this steady. Now then, if I just move it, flip it over, have a look on this side. Yeah. Now there is a bit of a conductive surface still left on it, I think. Have a look, see whether I can get onto that edge there, but I don't think I can. This bit of, I might be able to measure its value from end to end to see what value that is, and then see whether I can source a replacement from KDI, and that's where the heatsink tab will be bonded to it there, this gunk. That could be beryllium for all I know, so I'm going to have to bag this now and make sure that it, you know, it's disposed of properly, but it does look to me like as if there's definitely some, I don't know, I won't say it's corroded as such, but it looks as if it's just got too hot and then popped. That looks like it's a solder connection there anyway. So, interesting. I'm just going to see whether I've got some little magnifiers. But I haven't, that will be able to better that. Might be able to go on those electrical connections and measure its resistance and then see if I can get something similar, but it'll be a dB, whatever dB rating it is. I was hoping it'd be written on it, but what I'll still have to do is have a look and see what the values of them are. Now, although it's a resistor, an RF resistor, it's not being used as a pi attenuator, because the on these pads the metal heatsink tab is used as the ground connection, the signal ground. So you've got a resistor being a pi across the input, or then another resistor across the output, and then one in series, and each resistor element then will go to this tab here, which will be like the RF transistor bolted to the signal ground, the chassis, to wick the heat away, but it will also form an electrical connection for the pi section of the attenuator. In this configuration, the heatsink backing on it, which is also the signal ground connection, is not connected to signal ground. So either it's an attenuator that they're using just as a series resistor, but not as a proper attenuator, but just the resistor, because it's a high powered resistor having this heatsink, or it is an actual RF resistor at 50 ohms, which is from left to right. Normally the 50 ohm connection will be from one tab to the ground, signal ground tab, whereas this has got two connections, so it's rather like a pi attenuator. So I'll need to do some measurements, I think, on these to see whether it's just a straight through resistor that's on a high powered heatsink tab, or it's a pi attenuator. And if it is a high powered resistor, I should be able to buy them. They should be available. I think KDI sell them, and Element 14 and what have you, so I might be able to get some of these and then just replace this one that's broken off here, and that'll obviously then restore the feedback. So yes, very interesting. But I think as well we may still have a problem with this transistor, with the feedback through to the gate through the transistor. I'm going to have to look into that a bit further, because it might be something or nothing, you know. It might just be the internal resistors matching network that's used in the transistor which allow that to happen. So it could actually be working fine, but it's just that the feedback arrangement's dropped off, so it can't get any feedback, because it's obviously doing some amplification. In other words, for RF to come out, if this transistor was totally shot, we'd have lots of RF going into it and sod all coming out, and that's not what's happening here. So, you know, I need to be careful about writing this off yet. Besides that, the resistors are cheap in comparison to the transistors, so we can always replace the resistor first, find out if that solves it. If it does, then we can then go on to look at the replacing the rest of the resistors on the rest of the amplifiers. But it's strange, you know, that they've all got this problem where this little heatsink thing's dropped off and landed down here, and that again, that is just flapping about in the breeze. So is it a 100 ohm resistor, and that's dropped off of that. Perhaps it has. So it's probably a 100 ohm power resistor, because that looks like that would be on top of that. So I reckon that's what it is personally, but you never know, dear. We'll have a look. Might be able to buy those and get this amplifier fixed. It looks like we'll be needing 3 or 4 of them anyway, no matter what. Anyway, as luck would have it, Mouser sell them. I've had a look on eBay, there are some like them, but although that says 50 ohms on it there, it is actually the 100 ohm. I just come out of that, view product details, and then they do the 100 ohm version of them as well. So data sheet, let's have a look at the data sheet. Here we are, look. 50 ohm and 100 ohm versions, because in the listing it said that there was 100 ohms. They're about £10 each. A lot cheaper than any Rohde & Schwarz resistor, I'll tell you that. Any Rohde & Schwarz fanboys out there, watch my Rohde & Schwarz videos, you'll know how much resistors cost from them, especially for the RF side. So yeah, that looks like as if it could stand a fair bit of power as well. Let's have a look, power rating. Do a 50 ohm, 100 ohms, resistor 100 ohms, standard other ohm values available. 20 watts of power, you see. So that'd be nice to have that one. Could have some of those, this type as well. So a different mounting arrangement. That might have been better actually than the one that Kalmus have chosen. Again, this one here, this one's 25 watts. This one can stand. So 50 ohms. So in this current format with a lead, normally this lead here would be removed, and you just have a lead on the left, and the tab, the heatsink tab, would be signal ground, so that the resistive element would be between the tab and the ground here. But on these, what they've done, the ground is isolated electrically from the resistor element. The resistor element is across the 2 tabs. Now normally in attenuators, RF pi attenuators, you'll have one resistor from this tab which connects electrically to the tab. Then you'll have a series resistor that goes across the white bit, if you like, and then the other side, the other tab on the other side, will have another resistor again which will then go to the tab itself. So it's obviously in a pi formation. So it relies on the tab being the signal ground bolted to the heatsink, and you've got an in and an out. So you can get feed through 50 ohm resistors as well, where they're in this format, but they have one 50 ohm resistor internally which is then bonded to the heatsink tab as well, the signal ground tab that bolts to the heatsink, and these 2 copper leads are connected to each other internally, so they'll read 0 ohm short between end to end, but between the either end of the tabs and the big ground heatsink lug there'll be 50 ohms. So you've got to be really careful when you choose these devices that you choose the right one. These are just 50 ohm 50 ohm resistors, load resistor between these 2 copper tabs on left and right of the device. But again, Mouser sell them in different formats, different price ranges as well. So I think AliExpress have got them, so I might order with them. But these look like the sort of right sort of components. So yeah, they do look like the right sort of components. And they're only £10 each, plus VAT. In the UK it's 20% plus, you know, shipping, so these might be round about £15 each yet. So it soon adds up, you know, when you're looking at these sort of things. I think we had there was some others as well. I think AliExpress had them as well. There, look, AliExpress, they've got them. So, and they're only $2.80 each. But it does say dummy load resistors there. 250 watts, but they'll be big things, you know. So it's getting the right components, you know. That's the sort of thing. But again, I think Element or Mouse or whatever will be probably the best bet in order to order them from there. Okay, so the parts have come, and that's what they look like. These resistors from Mouser that are rated to 10 watts RF. Now, rather than just put those in, you know, across these terminals there and solder them in, I figured they look like they need a heatsink like the originals do, because there's a bit of a solder island in the middle, which is not electrically connected to either end. It's just to be soldered to a heatsink surface so that it can dissipate the heat. So what I've done, using some of this heat tape, is I took the original resistor heatsink and I covered the ends of the plate up with this heat tape, and then I've put some solder on the middle land, if you like. I don't know if you can see that down there. I know it's not very good, but I've done my best to try and solder it, you know, and without damaging the resistor. So that's nicely soldered in the middle, although it's a bit wonky. It's the best I can do at the moment. And the ends then are insulated to stop the edges of the resistor from touching the back plate while it was soldered, so I can remove those bits of tape after I've soldered it in place. But that means at least then, you see, it's using that heatsink tab as a way to dissipate the heat from the resistors. So then I just need to solder those resistor ends now into there, just introduce it, you know, where the original one went, and solder it on. Hopefully that'll work. I don't think, although these are rated to 10 watts, it doesn't say that they need to be heat synced to get 10 watts rating on them. So I'm unsure at this stage whether they would survive without the heat sink. They probably would, but I could always try it, I suppose, but I don't know. I think the power rating on these has probably got something to do with the fact that they'd be bolted to a heat sink, you know, of some description. So that's what I've done there. So I just need to tidy that up a little bit, but at least it's soldered down to the back plate, and then that should stop any electrical shorts with this tape. And then also it's got some heat dissipation as well. So now we see how it goes, can't we? Okay, so we've soldered it in now, and what I've done, I've just soldered it straight to the lands on either side, obviously on both sides there. So we're good to go. It's nice and solid as well. So, and there's no electrical connection between this side and this metal plate and that side and this metal plate. It's isolated. I've just checked it, and we've got 100 ohms between there and there. So this resistor is now connected. It's got a heat sink on it. So my plan is now, just as an experiment, is to run this up now and see whether, you know, it works. So we'll connect an input plus 20 dBm there and see what power we get out here, and adjust these bias pots to see what we can accomplish, and then see how hot that gets. Because if I touch that with my finger when it's doing the correct power, so we won't get that far with it. If it's not really hot to the touch, and we might not need that heat sink on the next amplifier, the resistor might be able to cope on its own. Because I say the resistor is rated at 10 watts RF power, but the actual amplifier might only be doing 3 watts, so may not need the heat sink, which would be better if I didn't have to add that to it. but we'll check it now and see what happens. What I'm trying to avoid though is a resistor getting that hot that it unsolders itself and drops off the board without the heat sink. So that's what I'm trying to achieve. So anyway, we'll do some measurements now. Okay, we're ready to do our measurements. We make some adjustments as well as necessary. We've got the power supply turned on at 26 volts DC. We've not got the output switched on, enabled yet. We're obviously supplying that power to this amplifier module that we've fitted the resistor in that we've received from Mouser. We've got the absorption watt meter, wave meter here, the Ray-Cordana meter, and we've got that on the 10 watt scale. So I'm actually looking, although we're using a test frequency of 100 megahertz at plus 20 dBm, just to get things going, what I'm looking to achieve in this measurement is I'm looking to the current meter to achieve a minimum current by adjusting the bias level with the maximum RF output power. And likewise, there's a little trimmer capacitor just down there. I'll see if I can zoom in on it, but it's just there. Look, that little trimmer capacitor. You can just touching it with my finger there. That's in such a location where I feel, I've yet to be proved wrong with it, that it's actually for the high frequency adjustment. So probably in the UHF spectrum. It's too small a capacitance and too close to the gate on that FET, power FET, to influence its HF, VHF frequency range. But we're giving a test frequency of 100 megahertz at the moment, but obviously a plus 20 dBm. But what we'll do, once we've got it going at 100 megahertz and got maximum out of it, then what we'll do is we'll adjust that little trimmer cap to see what effect that has after the biasing. And then we'll change the frequency of the signal generator then to 500 megahertz, which is in the UHF spectrum, but it's its halfway point of the radio spectrum, because this does from like 1 megahertz to 1 gigahertz. Now, from what I understand, the specs that I've seen on Kalmus amplifiers online, they don't actually have a very flat, not this particular type anyway, linear amplification across the entire frequency range. It does vary slightly. It's not exactly linear output across its entire frequency range, so that is obviously something we'll have to take into account. I've no alignment instructions, no service manual, no information on this amplifier whatsoever, so it's you know, tune for maximum smoke, see what we can get out of it. Hopefully it won't burst into flames, and the adjustment will work and we can get the amplifier going. So fingers crossed. Right, so what I'm going to do now, we're feeding obviously the signal in already, so I'll just need to enable the power supply, which is on now. We've got only a few hundred milliwatts there, so let me just see if I can adjust this potentiometer here. Let's see whether that's going down. The current's starting to climb. We're at 2.1 amps and the RF output power starting to climb. Just being mindful that when we peak the RF power, then which is about there, I've still got some adjustments. You can see the current's climbing, but the RF power's actually starting to dip now. So we just need to get that sweet spot where we've sort of got one eye, left eye on the current meter and the right eye on the power meter. And as the power starts to drop, which is about there, it's about the 2.4 amp mark there, I'd say. That's where we're achieving the maximum RF power. I'll try the next potentiometer. Let's see what we get with that. That's starting to go down, so can we increase it? The current's at 2.56. Now the RF's starting to go down, but the current's going up. So the RF's coming back up again slightly. But yet the current is about 2.4 amps maximum. Let's try the final amplifier bias. Now, if I can get the trimmer tool to go in, that's it. It's not making much of a difference with the current there. Nothing as such. Just keep turning it, see what happens. Nothing. No. Let's go back the other way, anti-clockwise. Oh, there we are. Look, suddenly up to 3 amps now, and very little output power. So we'll just get that to the sweet spot again. About 2.46 amps at that 1.25 watts roughly there. Right, I'll try and adjust that little trimmer capacitor now, and we'll see whether we can make an adjustment on that. That's not, it's having a slight effect on the current, 10 or 20 milliamps here there, but having nothing to do with the output power as such. So right, that seems to be, let's just go through them again just to see whether we can tweak a little bit extra out of them, but I don't think we can. Out there, I think we'll adjust the frequency shortly to 500 megahertz. So I'm obviously not going to get any more out of it, I don't think. I think I'm just wasting my time. So right, okay, we'll adjust it to 500 megahertz. 500 megahertz. There we are. All right, now we're getting about 2 watts. I'll just touch this. It's not even getting warm, that. Just lukewarm, that resistor. So maybe it doesn't need the heatsink tab on it after all, seeing as that's what it was rated to 10 watts. Right, I'm just going back on that trimmer capacitor. Ah, look at that. It's made a big difference, that. The current's gone up to 2.7 amps as well. And the trimmer toolkit's slipping off. So that's one way, right the way down. Then it peaks up again. The current's at 2.69 amps. And then we get it to about there. That's a sweet spot at around about the 500 megahertz mark there. 2 watts. Right, let's just touch this resistor. And it's not even warm, that resistor. It's just mildly lukewarm. So that's pretty good. We're drawing 2.7 amps, of course, on the power supply, with 2 watts output at 500 megahertz. Now, interestingly enough, if I drive the amplifier into compression, and then we start to increase, that's plus 25 dBm. We're getting to about 2.5 watts. Just keep going up. As high as the SIG-Gen will go. Plus 25 dBm at 2.5 watts. So let's see now if that makes any difference. It shouldn't do, but sometimes they do behave slightly differently for intercompression. And that's not having any effect whatsoever. 2.5 watts. Right, I'll leave it at plus 25 dBm. And let's just have a tinker with the biasing again, just to see what happens. Right. We're getting a bit more increase now. Look, in power. There, look. 2.5 watts. We're getting that at 100 megahertz, you see. Right. Let's adjust this. So we get an increase in current, but a decrease in RF power there. So let's go back the other way. We get an increase in RF power, and then it gets to that sweet spot, starts to go down again. So it's around about the 2.72 amps for peak power there. What about this one, the final drive? Let's just touch that resistor again. It's warm, but it's not hot by any stretch. So I think we're able to get away on the others by not putting the heat sinks on them, but we'll see. So that's current starting to climb again there, but yeah, little output on the RF meter, so it's declining. So let's get that back up again. Sweet spot again is around about there, and it's funny, there's no adjustment beyond that. So I'll bring it back to just round about there, I think, peak it there. at 2.73 amps for 2.5 watts. So if I can get 2.5 watts out the other amplifiers, we more or less achieved it, haven't we? Because it's 2, 4, 6, 8. Half a watt difference between that makes it 9, and then the other half a watt per amplifier extra on the other side, so that's 10 watts. So 2.5 watts is pretty good. Now I'll go back to 100 megahertz again. Frequency 100 megahertz, and we're at 2 watts there, so that's not too bad. It's still at plus 25 dBm, so if I reduce that to 20 dBm, then we're back down below 1 watt. So it has made in effect the biasing conditions at 500 megahertz, adjusting it for maximum power at 500 megahertz. I might have to set up like a sweep measurement where I'm sweeping the amplifier, and then see, I can increase the output power now at 100 megahertz just by adjusting these two bias pots. So I'm not sure what the alignment is on this, you see, whether we adjust it at 500 megahertz or we adjust it at 100 megahertz, but see, you're getting the power coming right back now at that sweet spot there. Let's take it back to 500 megahertz again. That's 500 megahertz, 2 watts. Let's put it at 10 megahertz. What output power is it doing at 1 watt? What's it doing at 1 megahertz? So that's 1 megahertz now, and it's doing 1.5 watts. So I'm a little undecided at the moment. I'll try 700 megahertz now. It's doing just under 1.5 watts. 900 megahertz, 1.5 watts. 1 gigahertz, it's doing just over 1.5 watt, call it 1.55, 1.6 watts. So I'm not sure with the biasing. I've adjusted it, obviously it's only drawing 2.54, it's not excessive. Seems more wide banded at that. If I frequency back to 500 megahertz again at plus 20, it's just under 2 watts. But the level, if I increase that then to plus 25, we're getting 2.5 watts still, so that's good. And then if I put the frequency back to 100 megahertz and then adjust the RF level again to plus 25 dBm, then we're getting 2.5 watts there. So it's more linear there with that adjustment. And then obviously down at 1 megahertz, then it's just decreased, if anything, just a smidgen. So at 1 megahertz, so now we'll jump from 1 megahertz at plus 25 dBm to 1 gigahertz. That's 1 gigahertz, and the power's more or less the same. So we'll go back to the level, we'll put 0 dBm, plus 20 dBm in, sorry, back in, at 1 gigahertz, which just gets us above 1.5 watts. And then what we'll do, we'll change the frequency then to 1 megahertz. And it's roughly about the same, just a little lower than that, a smidgen. But because we've jumped 2 massive frequencies, haven't we? We've jumped from 1 megahertz to 1 gigahertz, and then 1 gigahertz back to 1 megahertz again. So at this stage, I'm a little bit, I don't know what's the word, uncertain really as to what frequency we're meant to adjust the bias settings for on the RF output power. Certainly that trimmer capacity there, I think, needs adjusting around about the 500 megahertz mark for peak RF power. So I think we'll leave that as it is now, because it seems to be working. Obviously if I put the RF level up to, you know, plus 25 dBm, then we're well into the 2 watt region. So I'm happy with that, to be quite honest with you, because I know when the amplifier is driven harder, the output power is climbing quite considerably. But it's interesting though, if you adjust these bias pots at 500 megahertz and then you reduce the frequency down into the VHS spectrum, so 100 megahertz or lower, then the RF power goes just into the sort of half a watt region, a couple of 100 milliwatts. Whereas if you adjust the bias in more for the 100 megahertz frequency, but that little trimmer capacitor for the 500 megahertz frequency, then you can go between 1 megahertz and 1 gigahertz with quite a rough linear sort of region there. So that'll be interesting to sweep this amplifier at some point to see what flatness we're getting across the entire radio spectrum from 1 megahertz to 1 gigahertz. But I think with that adjustment that we've just demonstrated there, I can more or less consistently say 99% certain that it's going to be flat, because obviously we just proved that by jumping from the low to the high limits of the amplifier. So yeah, I'll move on to this one next. I've just got to solder one of those resistors in. I think this second one though, I'm going to, I'll just touch this again. It is actually quite warm now. I can feel it on my finger. It's not burning me, but it's not exactly warm now. It's getting quite hot. So the longer it's on, the more heat it'll dissipate. So maybe it is the case that on every one of them I'll have to solder this little heatsink tab on it again, you know, just to keep that continuity so they're all the same. That's probably the best practice to do. Okay, right, onwards and upwards. Right, so this is the heatsink tab off the oven. I'll put sort of a little blob of solder on it just to get it going. The idea is obviously that after I put a little bit of solder on here, you've got to be quick with this, because the chip resistor, with it being a ceramic type RF resistor, even when you solder on the end terminals, the heat conducts that quickly through that when you've soldered it on the middle of the device here, this island to there, the heat transfers straight to this middle bit, and then it can unsolder itself, and you've got to be careful with that. So you've got to be really quick when you're soldering it on. So what I'm going to do is I'm just going to bob a little bit of solder just in the middle here, just to tin it. That's all. Nothing too elaborate, but just to get some flow there. Oops. There we are. Right. So we've got that. That's ready to be connected up now, soldered to this middle land. So what I have to do now is I've got some heat tape, which I've cut off a roll, this special tape, which is this colour. And I'm going to overlay that on the back plate here, and then we're going to cut out a little square in it which resembles the square that's in the middle of this resistor. So naturally what will happen there is that there'll only be this middle bit exposed, and not the end bits. Now I could cut a little piece out and lay it on the resistor on this underside so it covers these two end bits up, because the end connections there need covering obviously, so that they don't touch this metal. That might be easier actually, come to think of it, and then just have a middle bit exposed. So I could cut two very tiny squares of this heat tape and overlay them on the ends of the device, and that way then when I solder it onto the board, then that should do it. Because how I do that, I'll solder it onto this heatsink tab rather, not the board. I lay the resistor on top, I put some flux on and everything and get it nice and ready for soldering. And what I do is I lay the resistor on the heatsink tab like that, and then I heat up the heatsink tab itself. I hold the soldering iron on the end of the heatsink tab. That then heats up the heatsink tab quite quickly actually to melting point, and then the resistor just drops down. You just see it drop down, and that's it then. Once it's cooled off and it's stuck to this this back plane. But then the only problem is then when you mount it in the amplifier, as you're soldering these end tabs, this has a desire to sort of drop off the resistor. So that's a bit of a pain in the backside. But anyway, if you're quick, either way, just one side at a time and then another side, just a quick dab with the soldering iron, then it doesn't get hot enough to desolder the heatsink tab off the back. So that's how I'm doing that with this. But I'm just experimenting, obviously, because the other one I actually laid 2 pieces of insulating tape on the edges, this heat tape here, which doesn't melt, you see, when you touch it with a soldering iron. It don't melt. It's special tape that's designed to withstand heat, and made in America, I think, by 3M, I think, or something. I'm not right sure, but it's really expensive tape. I think they call it Captain tape. Kilo Alpha Papa Tango Oscar November tape. Captain tape, heat tape it's called. So anyway, I got it at a bargain price, but yeah, Captain tape. I didn't write that, somebody else did, so it must be right. So there you go. If you need any, that's what you need to get. So I'm just going to have a faff about and see what we can do. Right, so we've cut little strips of, tiny little strips of, you know, Captain tape and stuck them over the ends. We've been very careful not to overlap too much. I do need a bit of overlap on the sides, but the ends, I don't want it overlapping too much on the ends. As you can see there, I mean, in relation to the size of my finger, my index finger, it's only tiny, so I've done that by eye. And would you believe it, I haven't needed to use my microscope in absolutely ages, and now that I need to use my microscope, I can't use it, because a few days ago when I cleaned up in the workshop to have some more gear in here, I removed the microscope, which is quite big and clumsy, to just put it in another room until such time as I can get it back in here. And now I need it for this, so I haven't been able to use it, so I've had to use my own eyesight with my magnifier lamp that I have here on the bench to get these pieces of tape cut and sort that out. But as you can see, it's so small. So the idea now, because we've got that little gap in the middle where the tape's not there, that will then solder to this tab in the middle, and we'll drop that on in a moment, and then we'll just get some flux on there, some flux residue, and then we'll just drop it on. I might put a little bit more solder on there, just build it up a bit, just so it gets a good bond, and then let's see how that process goes. It'll be a complete disaster, of course, at first, because sometimes you have to move it around. It misaligns, you get it nice and straight like that, and then as the solder flows, it suddenly does that. So we might have to faff about a little bit just to, you know, try and straighten it out. But this is what it's all about, improvisation. Okay, we've just put some flux on that, and just want to put a bit more solder on it because it's just a little bit flat. So I just want to, not too much solder, nothing too wild, but I just need it to be a bit more mounded, so that it'll sort of grab that resistor, you see, and pull it down. So that's nice. Got a nice little, it's a bit warm that, but yeah, it's a nice little mound on the top, which would be good. Then what we'll do now, you see, just put a little bit more flux on top. And this is where we get funny, because what I've done, I've put some flux already on the resistor underneath, and I'll just drop a little bit of, still fizzing a bit, a little bit of flux on that, and then what I'll do, just see if I can, where's my tweezers when you need them? Again, can't find those, so I might have to use my fingers yet. It's always a case with me, whenever I need tools, that I can't find them, you know, as and when I need them. But anyway, we've got this, so what I'll do is I'll just flip it over, and we'll just move it over to this. What I'll do, I'll just drop it down, without wrecking it, of course. put it round that way a bit more. Now this might go from one crisis to another here, but we'll see. I'll just move it that way a bit and just a bit more there. Now what I want to do, I just want to see it settle, that's all, which will be quite interesting. So let's have a look. Now I'm not too bothered if it moves a little bit, because I can always move it round, but I just need to see it settle. So I'll just need my magnifier so I can keep an eye on it. Right, just clean the tip. It's always difficult filming these things because you've got like a camera which is stopping you from getting your head too close, and you've got a magnifier light which you're looking through, which is behind the camera, and it's quite a considerable distance away, and then you're trying to gauge the soldering iron where that's going to be as well, and it changes everything completely when you're filming things. Right, I'm just going to hold that there a second. I'm just going to wait for that to drop. See whether we can get it to drop. I don't think it's going anywhere just yet. I'm messing it up already. This is what happens, you see. Try doing things. There, it's got it. I could see the solder, you can probably just see it there, look. It's bonded it. So, that should have done it. Just leave it to cool a moment. Just going to breathe on it and it'll fly off, and that'll be that. So we'll just put the iron back in its cradle. Okay. So next thing to do then is do a continuity check between the ends of this and the tab to make sure that it's not short-circuited underneath between end to end, or between each end and the tab, because obviously this is electrically isolated, or meant to be anyway. I think when I actually mount it in the amplifier, I think I'll turn the amplifier on, instead of it being mounted vertically like this, I'll turn it so it's horizontal like that, and then I'll solder this on top, so it means that the gravitational forces on this tab don't let it drop off a resistor when I'm soldering these resistors, if it's in a, like it is currently, you know, like that, where it can just drop down. So if I turn it this way, I solder it, it should prevent that from happening. I may even be able to go one step further and cut a long piece of this tape that will go through that hole round the resistor and back round, and stick it on the there we are, look. Oops. You see, I've soldered it down right in the middle. We'll just see that, hopefully, and it's nicely done. And then of course there's a heat tape underneath at the ends to stop a short circuit, allegedly. We'll find out in a moment. And it's bonded underneath there, you see. But yeah, I could put like another piece of heat tape, which I can remove after it's been soldered, that goes round the back there, along the side, and sort of across the top of that ceramic resistor down, and then it sort of sticks the heatsink tab mechanically to the resistor, so when I'm applying heat to these ends here on the transistor, that it doesn't then unsolder this back plane, because it does happen, it happens really quick as well. So we've still got that overhang of this heat tape just over the edge to prevent any solder from shorting out onto this. So that's how I planned it to be. Same at that side as well. So it'll just be those ends there then that'll be exposed to the electrical connections. So what I'll do now, I'll have a look at the resistance using the meter and see whether or not we have a problem. So I should just get my probes. I've got this probe and this probe. Right. Let's have a look here. Right, okie dokie. Let's get our friend the flute meter to the picture. And we will connect the black probe into the COM port and the red one into A. Right, let's have a look here. Right. Okay. That's our resistor down there. Okay, select ohms, which it's already on. I'll just touch the probes together at the end just to see whether they're short circuiting, which they should be, so there's no problems there. It's 37 ohm. Oh, there we are. Just these probes are a bit tarnished at the end, that's all. Let's just make sure that reads right. There we are, 1.1 ohms. Good as damn it. Right, okay, so I don't want a short circuit between the tab and the just have a look at this underneath my magnifier, otherwise I can't see what I'm doing. Right. So I'm going now between, what is the tab, and then each end of the resistor. So I shouldn't get a reading if I've soldered it properly. So there's no reading there on that side, and then on the other side there's no reading either. But between end to end I should be getting 100 ohms or thereabouts. And I can get on the ends. I keep slipping off the probes. Oops. So difficult sometimes to get onto things. These probes are not very good, I'm afraid. I'll have to treat myself to some new ones. Right, try again. Would you believe it? The leads covering the display. Try again. Right. 99.4 ohms. There we go. So we're good to go now to put it into the actual amplifier. So that's good. I'm happy with that. So I think I've done pretty well so far there. I'm not exactly, you know, I've got the precision machine skills and things that some people have, but I think I've done pretty well mounting that. I've kept it nice and straight against the back plane, and it's soldered nicely, and it looks a professional job to me, that. So all we've got to do now is get it in the amplifier. I'll put some flux on the ends as well, and then we'll put it late on the amplifier where the lugs are that come from one side from the gate and then the other side from the drain source tab, so I can just drop quickly, just touch like that with a soldering iron just to get it bonded, and then clear off after that before this melts and this all drops off again. That's the plan. Right, we've added that now to the amplifier, the second amplifier. it went in quite well actually, and it's got that nicely soldered in. Everything's nice there. Measured 100 ohms as well in the contact points where it's meant to be, so that's proved that. Now what I need to do now, once we get this amplifier up running like we did the other hopefully, and we can adjust the biasing to get the right output power, need to talk about measurements, because we've got a couple of options here. Because at some point what we're going to have to do shortly is we're going to have to sweep these amplifiers from 1 megahertz to 1 gigahertz, and we're looking to look at an output trace on a sweep analyzer, on a spectrum analyzer or an RF power meter in this case. But we're going to look at both of these next, these measurements. But we're going to have to adjust these amplifier biasing and this little trimmer capacitor up here to optimum, to flatness across the frequency range of the amplifier. Now, as you can see in this case, these amplifier transistors have feedback arrangements on them. Now that can cause a bit of a problem for spectrum analyzers, particularly when you're dealing with high powered RF amplifiers, where a spectrum analyzer such as the one that we've got over here, these spectrum analyzers don't like RF power going back in from the output port, and so any RF power at a substantial level coming back in will damage the spectrum analyzer. So what we need to do is be very careful of being able to connect a spectrum analyzer track gen output straight into an RF power amplifier like this, because the RF feedback will come back up into the spectrum analyzer input and then damage the spectrum analyzer, and that's what we don't want to do. So that's where you've got to be really careful. Now, the IFR Aeroflex 20, whatever it is, 25, whatever, SIG-gen has a feature on it where it can turn into what's called a sweep gen. So we could sweep the frequency from 1 megahertz to 1 gigahertz back and forth, and we can set the time rate for that. The output of that then will go on the purple cable to the input of the RF amplifier under test, and then we would have a 30 dB attenuator probably on the front of the spectrum analyzer. We would set the repetitive rate on the spectrum analyzer to slow, so we can see the performance of the amplifier. The problem with that is because we're setting its repetitive rate to a very low sweep, and it'll infill the display with the peaks and troughs of the amplifier at that moment in time. As we adjust the amplifier, then we'll have to wait for the sweep to come back, and if it's already infilled prior, you won't be able to see a trough in the area that's being infilled. It might be able to, it all depends how it graphically displays that repeat sweep, but ideally the best way is to feed a signal out from the track gen output into an amplifier, and then that amplifier then drives this amplifier here. So the best way to do that, which having thought about it, is to use another thing as well I forgot to mention, is this SIG-gen track gen output on the spectrum analyzer does not go up to plus 20 dBm, which is a level needed to drive these amplifiers. So we need to use a preamplifier. Well, I have another Kalmus amplifier here I could use, but rather than do that, what I'd like to do is use the integral preamp that's in the unit already. So I would feed in a 0 dBm sweep from the spectrum analyzer in here. I would power this up as it would normally would be. I would have the output of that amplifier then fed directly into the input of this power amplifier. So then we haven't got that problem of RF power from the feedback making its way back to the track gen and causing problems with the spectrum analyzer, which is the last thing I want. This preamplifier will amplify the spectrum analyzer's tracking generator level from 0 dBm to plus 20 dBm across the frequency range of its design, which is 1 megahertz to 1 gigahertz, and that will then allow us to sweep this amplifier with its full output power. Obviously the output power will be in excess of what the spectrum analyzer can cope with, so we would need to feed that into a 30 dB attenuator, which I have, or maybe a lesser depending on what the power is. 2 watts to 1 watts. Well, the maximum input power on the spectrum analyzer is 1 watt maximum, So a 3 dB, if we had 2 watts coming out of here, we'd need a 3 dB to get it to 1 watt. But bear in mind that's a maximum level that the spectrum analyzer can take. So potentially a 6 dB at 2 watts then would half the power from 2 watts to 1 watt for 3 dB, and another 3 dB, making it 6, would half it from 1 watt to half a watt. So it would basically halve it twice with 6 dB, because don't forget, for every 3 dBs we attenuate a signal, we half its power. So that's something that we can look at. If it's doing 3 watts though, perhaps we want a 9 dB attenuator in, for example. So we might be able to get away with a 6 dB, but again, we're using the upper limits of the input level to the spectrum analyzer, and we don't want to do that. I always like to work well below the maximum permissible input level on a spectrum analyzer for obvious reasons. So I might stick in, say, a 10 dB attenuator, something like that. We can then compensate for that attenuation in the spectrum analyzer, because we can set the spectrum analyzers we've done on my other videos to compensate for the external attenuator. There's a setting on there where you can change it to take account of the external input attenuation, so then you can read power directly on dBm, etc. on the display of a spectrum analyzer. So we can perhaps have a look at both actually, just to see what the differences are and what have you. So in either case, I can feed signals out at 0 dBm from both of these instruments into this amplifier, and then sweep its frequency range using the preamp that's already built in the unit, and that way we're protecting both instruments from power going back. Obviously it's only a small level of power, but the problem is it can cause interference and spurious emissions on the output of a SIGGEN in particular. I'm quite lucky that the SIGGEN, the IFR SIGGEN, has actually got a high level reverse input power back in, something around about 20 watts I think it says, reverse power it can take, so it won't damage that SIGGEN. It's obviously not desirable, but you know, it won't damage it, whereas it would with the spectrum analyzer, because that's not designed to take that kind of reverse power back, you see, up the track gen output. So that's what we need to be careful of when we're making these RF measurements. We don't need to consider that if there isn't a feedback arrangement on the RF amplifier. So like the other Kalmus amplifier that I've shown in this video, that doesn't have a feedback on the first stage, whereas this does. So there's potential there for quite a bit of RF power to be coming back, and it obviously could damage things. So that's what we need to avoid. Okay, so just to illustrate that then, if we look at this in greater detail, there's two ways we can do this. Obviously, we've got an RF power meter as well that's got a attenuator built into it, and it's basically got a 30, what does it say there, 33 dB attenuation on that BNC output, so that can be fed off to a spectrum analyzer as well as reading power on here, which is quite useful. So in this context then, if we look at for example the IFR SIGGEN, okay, now that can be programmed, as I say, to provide a sweep frequency from 1 megahertz to 1 gigahertz. Okay, now it can sweep along that entire frequency range, and obviously then we can look at this band here, and we can set the amplitude level, with that being the frequency and that being the level. We can set the frequency from 1 meg to 1 gigahertz, and then we've got the level. We'll set that, for example, at 0 dBm. So the output from that then will be fed into what is the preamplifier, which is in this Kalmus amplifier, and so that, as we know, has a plus 20 dB gain in it. So that amplifier provides plus 20 dBm output. Okay, so in turn that then would then provide an input then into our device under test, which is the RF power amplifier stage that we're looking at. Okay, The output of that then can be fed into the absorption wave meter, or the RF power meter. So that then is our little dial, RF power, where we've got the meter on. Now integral within that, there's actually an internal resistor, or a RF power attenuator, which then can feed an output signal then from that RF power attenuator, as well as getting an analog display. We can feed that then into either the spectrum analyzer for further analysis. Okay. Now, upon doing that, what we've achieved there is we've set the signal generator to sweep this frequency range here. We're amplifying that level from what is 0 dBm on here to a plus 20 dBm output, which is sufficient enough to drive this then roughly at this stage here to 3 watts RF. Okay, roughly, depending on, you know, obviously what it can do. We're attenuating that signal further, as well as reading the full power on the analog scale on the meter, and then measuring it on the spectrum analyzer. So on the spectrum analyzer, we're also looking then to see what is the bandwidth of the amplifier. Now, obviously, with the spectrum analyzer used in this context, it's going to be sweeping the spectrum analyzer in its own rate up and down the frequency range. Now, there is an output from the SIGGEN, a timing output that you can connect to the spectrum analyzer, and that will then synchronize the spectrum analyzer sweep rate with the SIGGEN. So you can do that, or alternatively, if you didn't use that synchronization time sweep, then you could just slow the sweep rate down at the spectrum analyzer and get it to infill in as a slow repetitive rate what the RF level is on the display. So this would display something like that. But then the issue is then, as we adjust the biasing on the device under test and this changes, it takes a while for characterization to suddenly show up. Now, whether that's a higher level or a lower level, and it takes a while for it to infill. And obviously, as we're adjusting this, we're making real-time adjustments, so we need to be able to do that quickly. So the other method that we've just discussed as well is we use the spectrum analyzer. Now, the spectrum analyzer in this context will be used as the source and the receive of the output signal from the amplifier. So we have spectrum analyzer again, the display. We have a track gen out and an in, so that would be out and that would be in. So we'd feed the output then, obviously, straight into the Kalmus amplifier, which has got an integral preamplifier in it, which we know gives plus 20 dBm. Now, this would be a 0 dBm again output from the track gen, and then we would then feed the plus 20 dBm into the device under test, okay, which is this amplifier that we've been repairing. Now, the output from this device then will be fed straight back to the spectrum analyzer, and that way then all the time synchronization is all in as it should be, and we feed that then in to the spectrum analyzer, and that way then we're getting the amplifier to sweep a frequency of 1 megahertz to 1 gigahertz. It looks like we're going to be joined by the technical manager in a minute, I think, because he's moaning. But anyway, it looks to me like as if that might be the best option. We can have a look at this one as well, but I think that's going to be the best option because that's real time. So as we're adjusting the biasing conditions in the amplifier and the device under test, the trace on the spectrum analyzer is going to change immediately, and there isn't going to be a time delay or a lag. Obviously in this scenario as well, where we can connect the time output from the SIGGEN to the spectrum analyzer, that would still be relatively quick, and it is possible, but it's a lot easier to do it in this way than it is that way. So we can have a look at both anyway, as I say, but that's just how we're going to look at this and see how we go, and that way it achieves a more of a flatness across its frequency range than just checking it at spot frequencies. So that's what we're trying to achieve, trying to get it some form of linearity across that frequency range of 1 megahertz to 1 gigahertz. Okay, so we've chosen our test setup now from the IFR signal generator. We're feeding the sweep frequency in on the input on there. We'll enable the output now, so we can now see the power reading on there. I've set the IFR signal generator to move 50 megahertz increments from 1 megahertz to 1 gigahertz at plus 20 dBm, and that output power's being read on here, and it takes 3 seconds to do a complete. Each time it moves from one step to another, it's 3 seconds. This BNC output from the minus 33 dBm attenuator in there is now being fed into the spectrum analyzer. I'm just going to put on the spectrum analyzer now the max hold. I'll just clear it at the moment and press max hold. So now we've got on the spectrum analyzer a max hold setting. So if I just remove this camera and take it over so we can see, this is between 1 megahertz to 1 gigahertz frequency bandwidth, and now we're measuring what is the amplitude, and to look at its linearity across the range. Now obviously it's moving at 50 megahertz increments, as you can see. 1 megahertz down here, 1 gigahertz here, and it's starting to tailor off. Don't worry so much about the lower signals that you can see down right at the bottom in between sometimes. They're the tones, the harmonics from the fundamental. As you can see, it starts off over here, goes up slightly, and starts to come down, and then starts to go up and then down and then up again. So that's what when we do the adjustments, we want to be able to try and get this as flat as possible across its entire frequency range. But that obviously, if I just clear, and then we can see that each time it does a 50 megahertz. These are the tones from the fundamental, and those tones will carry on, obviously, the harmonics. But that's the level there. So that's just giving us a quick example. I wanted to do it slow so it's easier to comprehend and easy to see for those who don't know. But yes, that's what we're looking at achieving. Now obviously when we use the track gen output from here into the preamp in the Kalmus, and we're sweeping it really quick, we'll get a line rather than these individual peaks. But to set up the IFR track gen was a nightmare, to be quite honest with you, because it was under menu, and then you've got the frequency sweep, select, and then we had the carrier sweep parameters, select. So there's a 3 second one. I might change that to 50 milliseconds and or something like that, which I think one of these buttons, there we are, look. And then you have to go down to sweep control, select on that, and then start it. So it's racing up and down now, the frequencies, so we'll get more of a definition on there. But obviously the time base on the spectrum analyzer has got to catch it as it's going up throughout the frequency range. So if I clear that, you won't even probably be able to see it. It's dancing about that much, you see, racing up and down. But you can more or less see, if you keep your eye on the peak as it's going across, you can see it's just going up and down a little bit. So UA, max hold A. And we can see as well on the analog meter, it's differing all over the place depending on what frequency it's on. So this is where we need now to achieve that measurement through using the track gen output on the output there. But we can see in particular at lower frequencies starts off about 1 megahertz slightly low, then builds up, then comes down at UHF and then up again. If I use the markers, and then we can have a look at that. So that's 200 megahertz, that peak there. So that's when it tends to be its most high performance, and then obviously at 300 megahertz upwards, then it starts to fall off, as we can see there. Particularly, I'd be interested to see what around about 500 megahertz again. Let's have a look here. 600, 500 megahertz is its lowest, roughly in the middle there. 300 and 552 megs, 500 megs, roughly. So yeah, it's giving more response at low frequencies. So that's what we're achieving now. We're trying to look at its bandwidth over its entire usable frequency range. So I think we'll come back next with the measurement where we're using the track gen output to sweep the amplifier, as opposed to trying to use the sweep gen facility on the IFR. I think that's what we'll do next. Okay, now we're ready to do a measurement of the amplifier, all connected back up with the power. So we're going to be using the internal power supply within the Kalmus amplifier itself now, rather than the external signal supply. So we've reconnected here the amplifier supplies and everything. What we're doing now is we've set up the spectrum analyzer, which we're going to go through in a moment, how to set that up to do this sweep gen. But just to explain what we've done, we've got the tracking gen output, which is the gold connector there, feeding, or we're going to set the spectrum analyzer up in a moment to feed a signal sweep between 1 megahertz and 1 gigahertz. So 1 gigahertz bandwidth sweep at 0 dBm output. We're choosing 0 dBm for two reasons. The first reason is that's the input level on the amplifier. Secondly, this track gen cannot produce plus 20 dBm, which, as we know, we need that to be able to drive these. So in order to overcome that problem, we have to maintain a 0 dBm output, but similarly within the unit itself we've got the preamp down here, this box, which is just there. Now that box, its input is fed to the N-type socket at the front. Its output would normally go to an input combiner splitter, which would then split 4 signal paths to each amplifier, obviously one to each amplifier. So what I've done is I've basically taken the output of the amplifier, the preamp, which is a variable gain preamp depending on what we set the control at the front here with. When we adjust that, its gain output increases or decreases accordingly. So I've isolated the output of that preamp, which is this silver cable that you can see coming out, and that output then is a single output instead of being split into 4, and that comes into this amplifier here on the input. So we're using the preamp now as the basis for driving this amplifier with plus 20 dBm, because we're sweeping a signal in through the front socket, 0 dBm at 1 megahertz to 1 gigahertz sweeping. We're amplifying that to plus 20 dBm, which is then entering this amplifier and driving this amplifier as well with the correct level. Indeed, it's powered from its own internal power supply as well, so we've no need now to connect any external power supplies up. The output, the RF power amplifier's output then is on a short cable, which then goes into what is this Micronde 30 dB 10 watt rated attenuator, which is that device there. Now we use that to protect the input of the spectrum analyzer. Obviously, if a spectrum analyzer is overloaded on the input, where it can only take 1 watt maximum on that port, then it would blow the spectrum analyzer. And in some circumstances, depending on how RF amplifiers are driven, the voltages are supplied with, and the tuning of the amplifier, can mean that sometimes they can produce rather unexpected output levels at particular frequencies, and it's something that can be easily overlooked, and thus you can potentially feed many watts into the front of the spectrum analyzer and damage it. So to protect the spectrum analyzer, we've got a 30 dB pad in on the input there. So what we're going to do, we're now going to tell the spectrum analyzer the parameters that we need it to work within, and we're also going to ask the spectrum analyzer to take account of the 30 dB attenuator on the RF input. We're going to set up the sweep gen, and we're also going to then measure the level in watts on the front of the spectrum analyzer using the markers, and we're then going to be in a position, once we displayed that information when the amplifier is turned on, to adjust the biasing pots that are in these amplifiers to get as linear response as we can across its entire frequency range of 1 MHz to 1 GHz. So let's do that now. I might need to adjust the lighting here in order to better this. So if we just go to our friend on the front panel. So first of all, we'll set up the frequency. I'll just see whether that lighting makes any difference. I think it does, yes. So let's see if I can see the buttons with my eyes. So first of all, we'll set the frequency. Now we'll set the start frequency to 1 MHz. Okay. We'll set the stop frequency to 1 GHz. So that sets our bandwidth up at the moment. We then need to go to the track gen, which is AUX control, select tracking generator, and then we need to select the level. At the moment it's minus 10 dBm, which is too low. So we need to select 0 dBm, and I think that's the dBm button, yeah. Then we need to turn the track gen on, so the underscore is on the on section. So that's now generating a 0 dBm signal out of the track gen output port between 1 MHz to 1 GHz. It's now sweeping that. Now what we need to do, we need to tell the spectrum analyzer that when it's making a measurement under amplitude, that the RF attenuator, which is this 30 dB pad, is present. So any levels that we wish to measure cancel out this 30 dB's input attenuation, and thus read the power as an effect as it would be if the power was fed directly into the front. Obviously that would then allow the spectrum analyzer to read greater power levels than it can currently take on its input port alone without an attenuator. So we would need to go to, I think it's reference level offset, and currently it's at 0 dB. We'll need to change that now to 30 dB in line with the level of attenuation. This attenuator is marked on the top with 30 dB, so we know that level. If you change that attenuator to any other value, then we would need to input that as well, so that the spectrum analyzer has got the correct reference level. Okay, we're now nearly there. So the only thing we might need to adjust is the amplitude as and when the signal is being produced into the instrument, where we'll need to attenuate it somewhat. So the reference level at the moment is 30 dBm reference level, taking into account the 30 dB attenuator. So now we're ready to rock and roll. Now what we can do is we can now switch on our amplifier. Now I've wound the gain down to minimum. We'll switch on the amplifier. Okay. Right, so before we actually wind the gain pot up, what we'll do is we will introduce under the amplitude, because it's more sensitive at the moment, maximum level of attenuation on the spectrum analyzer. Now we're going to adjust the gain pot on the front, the power control on the front of the amplifier. Okay, right. So that's now at maximum level. Okay, so that's what we've adjusted there. This control, we've turned that to maximum. So now we've adjusted the spectrum analyzer accordingly. Now I switch that off. Okay, so now we need to go to measure the signal. Now we can measure it in two ways. We can measure it directly in dBm, or alternatively we can measure it in watts. It's entirely up to you how you work. But before we do that, we can see straight away that the start frequency is 1 megahertz and the stop frequency is 1 gigahertz, and you can see it's actually quite flat is the response. Excuse me, coughing. So that's actually very good. There's a few little ripples in it, but not great ripples, not huge dips and gain and attenuation. It's not going all over the place. It's not wild. So let's have a look at that in greater detail now. So if we go back to amplitude, I think if we go to units, is it? I think it might be. Maybe not. Where do I get to that then? Is it on? It's not under span. It's not under frequency. Where is it? Somewhere, I'll find it. This is the beauty about radio engineering. When you're working with different pieces of test kit, you need to be able to find things. It might be under marker actually. Maybe not. Where is it? It must be under amplitude. Linear attenuation, reference level. Oh, here we are. Look, I think it's this one. Amped units. There we are. Look. So now we can select between dBm, dB microvolt, dB millivolt, volts and watts. So we'll select watts. So there we go, watts. So the spectrum analyzer is taking into account 30 dBs, and now we're reading the power at the top there. We're currently at the marker frequency, center frequency of 500 megahertz. So I can adjust the marker now using the rotary control, or can I? Marker, there we go, look, right. So normal marker, if I take it right the way down to sort of, just barely see it under that line, that's 4 point something megahertz, and already we're reading 3.4 watts, and as we adjust the marker, that's now what, 24 megahertz, 3.1 watts. It dips a little there at 2.5 watts, which is at around about 55 megahertz, I think it is, 51 something, can't see it, it's just there. If I can just adjust this amplifier a bit, amplitude, maybe I might be able to get it past that. Right, now if I go back to marker, there we go, I can see the frequency now. Bloody trace was running right way through the figures. So right, okay, so we're back to where we were, 51 megahertz there. We've got 2.51 watts, 2.518 watts. So just the marker, let's keep moving that. We're back up to the 3 watt mark, most of it right up to 200 megahertz, 4 watt mark, sort of 3.5 to 3.8 watts roughly, 200, 300 megahertz. So we can see quite consistently the power is generally quite linear across this section, slight gains and troughs, but not wild, nothing wild. So what we can do, we can try and achieve more linearity by making some slight adjustments on the biasing on those devices, but those amplifiers. If I just don't know if we're going to be able to get it in the same frame, but what I'll do, I'll just go, if I find my trimming tool, which is hiding from me, I'll just go onto this bias pot here, and I'll just make some minor adjustments first to see what effect it has on the trace. So, right. So this is the very first stage amplifier now, and then we can have a look for just some slight changes in that. So I'm beginning to make an adjustment now, and it's starting to fall off at the lower frequencies, as you can see, and then the whole gain. So I'll turn it back the other way, and now we're getting more of a, you can see the whole gain across the entire band starting to drop there. So the peak is, it's looking at 3.68, 3.837 watts there. Starting to dip then again at the lower part of the frequencies. So I'll just adjust it back to there. Right, I'll move to the second stage, and let's just adjust that. So we're getting a little bit more gain across the whole band there, and then we're starting to drop. So back up again the other way, clockwise. Just getting up to that 3.837. Seems to be where we're at the moment, 3.837 watts. Then it starts coming down. So 3.837 is the most we can achieve there. Right, going to the final amplifier. I just need to be careful with the final amplifier because it can start to draw quite a lot of current, and I don't want to destroy the amplifier transistor. So the gain's going that way, and now the gain's going up a little bit that way. Now it's collapsing. 3.6, 3.837, 3. Yeah, it's starting to come down again now, I think so. Yeah, so I'll turn it back the other way because I can see it was just starting to die off. So 3.837 watts. So I'll go back to the second stage again, because that was the third stage, the final stage. I'll go back to the second stage and just try and adjust that again. 3.837 watts. Right. Much that, see, that's where it starts to drop off, and it's coming up just ever so slightly to about there. Can't get any better than that. Right, now that little trimmer capacitor that's on the input to the RF amplifier, we'll just adjust that. So if I turn that way, see, you can tell that's making a big difference. I'm just turning that counterclockwise now. As we can see, there's like a bit of a notch in it. So that's a maximum whatever or minimum capacitance that is in that turn, and then we start to go back the other way. So that obviously has an effect at the high frequency end, then it starts to come down again. So I'd say it's around about there is the best sweet spot for it. So I think that's about as much as we're going to get. If I alter the marker frequency up to the top end of the band, we're getting about 5 watts output. At the top end, at round about a gigahertz, 4.656 watts at 1 gigahertz. And then if we come all the way down, that's, what is it, the minimum there, looking at 3.8 watts roughly. It's dithering between 6 and 8 watts. And then Now what we can do as well, now we're at 57 megahertz, it's 2.6 watts. We can, if we wish. Unfortunately, the adjustments not making much of a difference on a minute micro scale within the smaller bandwidths. So this is as good as we're going to get linearity wise. But if it was a case that we could make smaller adjustments at the lower frequencies and other smaller adjustments at the higher frequencies, what we can do is we can change the start and stop frequencies then to drag out those smaller dips, and then we can fine-tune those on the system in order to try and linearize them instead of having the peaks and troughs. But the biasing conditions on this amplifier is as good as it gets, and there aren't any other tuning elements in the amplifier, as in inductors or capacitors, that can be adjusted to try and counteract any of the little troughs. But these troughs are okay, you know, they're not a major problem. So I'm very happy with that. So I think I'm happy we've adjusted that. Now if I adjust the gain to minimum, we can see that there's still some leakage through the amplifier preamp, particularly the higher frequencies. But that's to be expected, I suppose. But that's the maximum gain there. So I'm happy with that. Across its frequency range, I think that's acceptable. So what we'll do now, we'll go now to the first amplifier, and we will adjust this amplifier now, and we'll see what performance we get out of that one. Now if I touch this resistor, it's warm, but it's not majorly warm. It's not something that's gonna, you know, burn my hand off, so to speak. It's just lukewarm. This one, that's quite hot, is that one, that's quite hot, and that's reasonably warm. That's quite hot. That's lukewarmish, roughly. I'll say it's lukewarm. It's actually warm, is that. Quite hot. Not as hot as this one. That one's obviously doing a fair bit of gain, is that. Okay. So we'll transfer the cables over to the amplifier on the right and try again. Right, we've connected back up to the first amplifier, turn the power on, and we'll just increase the gain now on the RF amplifier, and we'll just do that now. So again, quite a nice flat trace before we make any adjustments. I don't think there needs to be an adjustment on that one. Now we could drill down into further detail, particularly at these lower frequencies where these ripples occur. If I select the marker and then adjust the frequency, we've got a little dip there, little trough, another trough there, 164 megahertz, 2.76 watts, another one about 50 megahertz before it goes up to there. That signal right at the end here, right at the end, is the internally generated one that HP Agilent spectrum analyzers tend to produce themselves. It's a common thing, so we can ignore that. Now I can, on the marker, I think it is, let's have a look here, can adjust it to see what the marker level, max marker level, I can adjust under amplitude, I think. Here we are. I can drill down into further detail. So we're looking at a 10 dB per division, but when we lower that, now we're at 5 dB division and then 2 dBs per division, we can get some more analysis now of what's going on. And I can just reduce that down. Excuse my coughing. Right, so now we can go to the marker, and we can see at 4.3 megahertz it's doing 3.5 watts. But if we then just adjust the marker and get it down into that little trough just there, it's doing 2.2 watts at 51 megahertz. And then when we get it up to there, 100 megahertz, it's obviously doing 3 watts, 3.1 watts. And then again down there as well at 157.5 megahertz, it's doing 2.6 watts. So what I can do using my trimming tool is I can adjust the RF amplifier now, biasing pots, these biasing potentiometers and that capacitor. So I'll start again as we did before, just adjusting the first, second and third stage and that trimmer cap just there, and let's see whether we can adjust that response. So let's go back to, what is this? Okay, so I'll look at the first stage amplifier, see what that produces. So I'm adjusting the, as we can see, it's going down the RF, now it's coming up at the higher, it's evening out a bit there, and starting to go down again at the lower frequencies. You see it dropping off. So I just need to get it as straight as we can from left to right. I've got my eyes currently at the moment right at the edge here to see, because I can see that as I do that measurement it's seldom making much of a difference. So that's a bit better there, I'd say. Yeah, just fiddling about there, I'd say, is the best that we're going to get it. Now if I just take the marker back down to there, just adjust that. Bring that up. So when you look at it across the board, we're getting a bit of a sag here. As that's coming up, this is coming down. So as you can see, it's just altering its characteristics just ever so slightly before then I'm going to alter it to about there. I'm quite happy with that response there. Right, I'll go to the second stage now, and just trying to get on the little screw in the end of the potentiometer. Right, so that's having a marked difference there. Let's say about there really. Yeah, it starts to drop off again there, look, so out there. Just making a few adjustments. And then the final stage amplifier. Right, so that's gone all together there. Now bringing that gain up. Now it's gone again. Gone again there. Gone again there. So just bring it round about. I'm just trying to even it out a bit more there. I think that's about it. As we turn it a bit more, it starts dropping top and bottom, and the whole of it starts going. Then we get about there, that's the sort of peak, and then it starts going again at the bottom end then as well. So let's just see whether we can just get to a happy medium. I think it's difficult because obviously I'm trying to look at the whole frequency spectrum at the same time. Let's say about there. Now let's go to the RF capacitor. the one that's a little trimmer capacitor, and see what we can get with that. Now then, just getting onto it. It's difficult to see it because it's so small and it's so far away. Come on. There we are, I'm on it. Right, so that has a marked change, and I've just slipped off the capacitor with my trimming tool. It's gone all together there, so I'll get it to come back up. So we'll just adjust that now to the marker, to amplitude, dB per division, and then we'll go back to 10 dB a division. So as we can see there, we get that notch effect again, and we get that. So I'll go just adjust that then. Right, so about there I'd say. I'm looking really to try and bring this trough up there. So if we go back to marker, and adjust the marker now, it's just in that little trough, 2.4 watts. Now if I adjust that, I'm happy with it there. I'm not going to better it much really. I can get more gain out of it up at the higher frequencies, but then it affects the rest of the band as well, down to about 500 megahertz, so I'm quite happy with that. But that's at 2 dBs per division anyway, so we're doing quite well there, I think. Others may disagree. Right. So now we're at 10 dB per division. As you can see there, we've got quite a linear response. 2.7 watts roughly. So I'll just have a look at the biasing again on the final amplifier. Can we get any more? Maybe across the band? Maybe, maybe not. No, I don't think we can. Let's go back to that 2 dBs per division. See there, look, it's collapsing, then we're getting a nice collapsing again, so it's about there's the optimum. Yeah. So 1 megahertz to 1 gigahertz, and then I think, so we're only getting 2.7 watts out of this amplifier. Just on the second stage there, I can't get any more gain out of it. 2.716 watts is about as much as we can achieve. Try the first stage again. So again, levels disappearing. 2.6 watts, 2.716, and then we start to obviously see the bottom end drop off. So it's about there, I'd say. So yeah, I don't think we're going to be able to better it. Definitely don't think. 2.76 watts. What I will do is I'll measure the resistors, the other two resistors on this, that one and this, to see what resistance they are, just to see whether they're 100 ohms or whether the values have changed. I've got one spare resistor. I ordered 5. There's 4 amplifiers plus I had one for spare, so it may be that one of those resistors is starting to go high and it might not be giving the right feedback. If so, we can replace it now while it's out of the, you know, accessible, because the next 2 amplifiers that's on the other side, I'm going to have to unbolt this entire assembly with a fan on right to the end, that entire exhaust thing, and take the whole thing off just to get to the other amplifiers on the other side to repair those. So this is doing 2.7 watts, whereas that's doing about 3.8 to 4 watts. So there's a gain difference between them both, which is quite interesting. I've also noticed just something a little bit, probably incidental, but if you have a look at the SMAs, the square on there, whereas here the diagonal, the fitted diagonally, I don't know why that is. You can see that difference between them, so I've no idea why they've done that, but might be something in nothing. I don't know, but yeah, I am quite pleased with the linearity on that. I think it's as good as we're gonna get, so onwards and upwards. Well, I'm just looking now at getting this out, and I thought that this unit, the bottom section and the top bit, was broken into 2 halves, and what it is, this bit's mounted on a plate which sits on the bottom, and it's held in by 2 screws at the top, which I've just removed, that are down there, one behind that white connector down there in the corner, and this one here, and then there looks to be a few screws along the bottom in this area, and I thought this could come away on its own, but apparently not, because if we look down there, you might just be able to see this tray continues the whole width of the unit. So basically the whole assembly itself, which is a real pain, that metal tray there, that's right down there, as you can probably see, that thing that's just there, this goes all the way down. You can probably just see in there, I zoom in. You can just see there, look, it carries on, it's not split, there isn't like a split down there. So what that means is, unfortunately, I've got to strip the whole thing out. I've got to remove everything, so I'd have to take all the screws out at the bottom, which loosens this entire innards, but then I've also got to remove all the plugs and connectors that connect to the front and switch, etc., and likewise the mains filter at the back, in order then for the whole unit to come away from the enclosure that it's in. I mean, we'll talk about bad design when it comes to maintenance. You know, the labour time involved in doing that, when you could have just had that separate on its own, fastened. Now, I can't see underneath when I turn it round any screws which are independent for this heatsink that sort of bolt through the bottom. They all seem to be, it's just these screws at the top which I've removed, and obviously these here down the middle, and then there's some more screws down at the bottom here which are for the other part of the plate. I was hoping that the heatsink itself assembly would have had its own screws through the bottom, and thus it would have been removable independently of everything else, but it isn't, unfortunately. It's all built on like a tray, a carrier tray, before it's then put in this enclosure. So that's how they must make it. They must make that, assemble it all together on this tray, which is this plate at the bottom, and the plate's the full width of the unit and length of it, and that's then fastened into this outer enclosure, which is the white enclosure that goes round it, which is just going to make everything a lot harder than it would normally be just to get that off. So, and obviously once you've got the tray out then from the enclosure, when you turn it over, there'll be screws then on the bottom of that plate that covers it all, that then go into the heatsink on here. So then I can remove that and remove that from the plate. So why they designed it like that, I don't know. It's obviously clearly not been designed with maintenance and repair in mind. It's just one of those things, I'm afraid. We'll just have to remove everything, strip it all down completely, because obviously these connectors as well will have to come off, because the sockets and on the front and the switch, because in order to withdraw the unit out, I have to bring the unit forward to clear the fan that's buried behind this lip, to then withdraw it, because this is a pressed frame. It's not like you get on a lot of equipment like power supplies where the front panel and the rear panel's held on with separate screws at the front and back, so you can remove those individually to the base plate. On this it's all moulded, as it's all just been pressed into one continuous piece of metal, so I have to remove everything at the front in order to get enough clearance so when the whole unit's brought forward it can then come out. Otherwise it's just going to catch that plate on these connectors and fuses, etc. So I've got to, and switches, so I've got to remove all that. I can't believe it. And then I've got to remove a load of other stuff as well in order to just get into it. So this is going to take a while, so back soon. Right, we've got the most inner part out, the main enclosure now. It was an absolute nightmare trying to get it out. You've got to remove so many things, including the main switch, push the indicator lamps that are at the front here out the enclosure, because it's an enclosure that goes quite close to the front underneath and then up here at the back. And so the only way you can get it out is to hinge the front up out the unit. So everything that's fastened to the front of the instrument all has to come out first before you can even lift this part up. Nightmare to do, really difficult, very difficult indeed. Anyway, now that we've got this out, it means now if I lift this up, which is still quite heavy, just trying to lift it up without causing any damage to any plugs or connectors here, but underneath you'll see there's some screws underneath which then fasten that heatsink unit down. So that's what we've got to remove now to get the heat sinks off. So obviously we can get into these two modules. This entire module then will come away and come off, and then we can get access. This is a fan bit that goes in the back. Bearing in mind, of course, the switch mode power supply in here, each one of these amplifiers takes roughly 2.5 amps to 2.7 amps, call it. So you're looking at a good 5 amps per side, so 10 amps quiescent current drawn, regardless of whether the amplifier is actually amplifying RF or not. So you're looking at, even before we do any amplification of RF, we're looking at 10 amps being drawn. So this is why it needs this really powerful fan which sits in here, blowing the air through it and making sure that, you know, it keeps it cool, otherwise it'll just have thermal runaway. So we'll remove this now and then get stuck in further. So having removed all these screws down here, which is ridiculous, you know, we've got quite a number of them there. We've finally got this module off, and of course we've repaired that side. We just now need to get access to these modules and repeat the process, but this is what's left. These connectors go to the RFPA stage, and then this is your power supply down there, which is made by Unipower, I think it's called, and gives us some data there. So it's a 400 watt power supply, and talks about input in amps, 7 or 4 amp, 120 versus 240 volts, so 220 to 240, drawing 4 amps, but at 120 volts it draws 7 amps. And then 28 volt at 14 amp output. So that's what we're looking at there. And it looks like as if as well the power control circuit for the preamp, which is this module here, I was looking to see if there was a transistor bolted on here, so that it as you adjust the potentiometer on the front, that it will control the voltage to this amplifier on that feed through. But it looks like as if it just comes straight through the pot, the potentiometer, probably because the load that this takes is quite small in current. But it doesn't look like as if there's a transistor, unless there's something hidden underneath there. But I can't see anything under there at all, so I don't know. Seems a bit strange. Maybe that there is something there, but I can't see anything anyway. Okay, so we've got the other side of the amplifier off now, the covers to expose those modules, and again looking inside we've got a very similar thing going off where we've got just on the left here, if we look at the RF transistor, the final output one there, this resistor that's just there, it's almost desoldered and dropped off, still hanging on for dear life, but that needs replacing. This has lost its heatsink altogether, that resistor, which is this here, just dropped off onto the floor of the module. That one's still okay with the look of it. So there's two things we can do here potentially: resolder them back if the resistance is reading correctly, but that one might be possible, but this one looks like it's got some of its conductive coating coming away, so I might just replace those. I think I've got 3 left actually, 3 resistors, because I got 1 spare, so I might be able to just replace those 2 anyway, because on this module these 2 look okay, although we've yet to measure them, and that one's lost its heatsink and its conductive stuff, so I couldn't solder that back anyway, and lo and behold the heatsink tab's there for that. So we might be able to just get away with the last 3 resistors that we've got and get it going again. So I think the next stage is to just measure those resistors to see whether they are 100 ohms each, the ones that are remaining in place, just to check their continuity is okay, and then just replace the 3 that we have that are faulty, and then try and measure the amplifiers again like we did on the other side. So having removed all these screws down here, which is ridiculous, you know, we've got quite a number of them there, we finally got this module off, and of course we've repaired that side. We just now need to get access to these modules and repeat the process, but this is what's left. These connectors go to the RFPA stage, and then this is your power supply down there, which is made by Unipower, I think it's called, and gives us some data there. So it's a 400 watt power supply, and talks about input in amps, 7 or 4 amp, 120 versus 240 volts, so 220 to 240 drawing 4 amps, but at 120 volts it draws 7 amps. And then 28 volt at 14 amp output, so that's what we're looking at there. And it looks like as if as well the power control circuit for the preamp, which is this module here, I was looking to see if there was a transistor bolted on here, so that it as you adjust the potentiometer on the front, that it will control the voltage to this amplifier on that feed through. But it looks like as if it just comes straight through the pot, the potentiometer, probably because the load that this takes is quite small in current. But it doesn't look like as if there's a transistor, unless there's something hidden underneath there. But I can't see anything under there at all, so I don't know. Seems a bit strange. Maybe that there is something there, but I can't see anything anyway. Right, the resistor that was just across here, which I removed, didn't have a heatsink on it. I've just resoldered it back on. I've just done that. As you can see there, it's been soldered quite nicely. All I've done is just re-tin both sides of the side of the resistor as well as the back plate, and then I've used lead solder with some flux, some paint on flux. Just laid the resistor on the top and then touched the solder down like we did on the one earlier, and then the chip resistor just floated down onto the back plate, and now that's ready to be reinstalled. As you can see, it's all nicely soldered back on, so that's pretty good. Might be able to do that with this one. So again, we've got still the back plate of the resistor available to solder, and this has dropped down, so it's actually turned round as well, if you notice, but might be able to do that with that as well. So I'll desolder that next and then put that resistor back in it, and that's that capacitor there. Look, I was telling you about earlier. If I go upwards, you can see there it's just horizontally, so easy to damage that, because you put too much heat on here, it'll snap off, it'll break off, and then you stuff this capacitor and you have to get another one then if that's the case. So right, onwards and upwards, as I say. Okay, so we've got the other one now. As we can see, the back of this resistor's still got some nice soldering land on it, so it's not too bad at all, this one. It's just really needs renewing. There's some excess solder on this, which we just need to remove, old solder. So we've got the paste desoldering gun. So what we'll do is we'll just to make sure we get as much solder off as we can, we'll just apply a little bit of flux onto there, just to get some liquefaction going when we put the desoldering gun on. So here we go. Just check it works. It's got some suction. Right then, so we'll drop it on there like so. Wait for it to get it all nice and hot and running. That's it. So there's less solder there now to worry about, which is always good. And I'll not bother sucking the solder off the resistor element, because obviously the excess heat could cause damage to the resistor element itself, simply because it doesn't have a heat sink. So what we now do is just grab hold of that, because it'll still be hot. We need to cool that off, because we're going to apply some flux, and we don't want the flux, which in my case is water based, excuse me, we don't want it evaporating before we use it. So with heat sinking away the heat there that's been generated, I do the finger test, it's not burning my finger, so that's good. Right, so now what we'll do, we'll apply some more of this flux, but we'll apply it to both surfaces. We'll apply it to the heatsink tab as well. Okay, so we've got a nice little drop of it there, quite a liberal amount. And then we want to just turn this resistor over, and then we also want to apply some to that too. Not too much, but just enough to whet its appetite. And then what we'll do then is we'll very carefully place that resistor upon its heatsink tab, and then we're ready to see it sort of float down then. So if we just pick that resistor up, and if I remember rightly, the orientation was for the tab to be facing upwards with that way around, if I remember rightly. Or was it that way around? Just trying to think. Yes, it was that way around there, like that. That's it, because it goes the opposite way. That's it. Because the side to the right, the tab to the right, goes to the up-ended capacitor, the one that's got the horizontal capacitor sticking off the board, and the tab to the left goes to the gate of the FET, and the hole at the tab goes towards the top of the device. So that's the correct orientation. Now, before we apply any heat, we just need to check to make sure that the resistor's in the correct orientation. So we can see there it's just a little bit over, so we'll just apply a little bit of, just move it a little bit, just so that we've got some. I'm doing this through the camera. It's much harder to do it through the camera than it would be otherwise. Right, we're ready to rock and roll. We're ready to just apply heat now to the heatsink tab with a soldering iron. So we've got the soldering iron. We're just going to gently do that. And then hopefully soon it'll just drop down like that. And then we just remove the heatsink from the soldering iron and leave it to cool down. Don't touch it or blow on it or anything like that, because it'll just fly off, as I say. So I'll just give it a few moments to cool. What we'll do, we'll just now that it's more or less set by now, we'll just heat sink it again, just cool it off, just to make sure that it's handleable and that the heat's gone away, plus as well that it's not going to burn my fingers when I pick it up, etc. So right, so let's have a look. So we can see it's nicely soldered down, and that's a pretty good job, I think. Soon it's all been hand done. So let's have a look. Pick it up with my finger. Have a look. I think I've pretty well got that lined up. I think you'd agree. So it's all nicely done, ready to be resoldered back on. So there you go. Now that we're having to replace this final resistor on the end there with this new 10 watt one that we got from Mouser, what we're having to do to protect the ends of the resistor, like we did with the earlier ones, from becoming short-circuited on the back plate, the end terminals, obviously the 100 ohm resistor, and the middle bit is the heatsink, the part that solders to the heatsink tab. So what I've had to do here is, like the other, I've had to put some heat tape, 2 bands of heat tape over the end, which will prevent these end terminals from short-circuiting to the back plate. And then what we're going to do, we're going to build a little island up on this middle of this resistor, on this heatsink tab of solder, and then we're going to put some resin, some flux here in the middle, and some on this resistor. And then when we lay the resistor on top, there'll be like 2 islands, 2 blobs, if you like, of solder that'll be touching one another when the resistor is laid on top. And then when we apply heat on the back plate, then the resistor should just float down like the other one we've just done, leaving the end tabs here insulated with this back plate. Now once we've done that, we can then chop off any excess tape or whatever, and then it'll just have these 2 little islands underneath, preventing any short circuits. So that's what we'll do now, because obviously this tape doesn't melt, it's a special tape. So that's what we'll do, we'll just solder this, and hopefully, fingers crossed, should work. Right, that's all of them done now. All 3 resistors in there, all nicely put back and soldered together, just likewise here. Same thing there. We've used on the last one here a new resistor, so that's done. And we're ready to do tests again on both these amplifiers. Before we put it back in the main module, what I'm going to do is I'm going to power it independently using the Siglent power supply over there. We'll power this up, then we'll inject the signal through onto the spectrum analyzer to check on the spectrum analyzer that the amplification on both modules works before we put it back in the unit, because the last thing we want is to put it back in the unit and find out, once we fasten it all back together, that the amplifiers don't work properly. So that'd be a good exercise to do before we do that. Okay, so we've set up the power supply now, providing power to our circuit. So basically we've got the preamp down there powered with 26 volts with the control potentiometer on the front of the enclosure connected. We've got 0 dBm, which I'm going to show you on the spectrum analyzer in a minute, coming into the preamp, plus 20 dBm leaving on this cable and going into the input, and into the input of the amplifier there. The output of the amplifier on this cable then comes across right the way down and then basically into the attenuator on the front of the spectrum analyzer. Now we've set up the spectrum analyzer basically to sweep 1 megahertz to 1 gigahertz like we did earlier when we did the other two amplifiers on the other side, and we've got the reading there in watts as well on that particular readout. Now what I've got in here, I think it is, let's have a look, see if I can find it. Got a trimming tool. So we've got the spectrum analyzer set up to produce 0 dBm sweep. I've just set the amplitude correct so that the tracer's not exceeding the top of the graticules. So what we'll do, we'll turn the power on now, and then we'll have a look at the bias adjustments, and like we've done earlier. So on goes the power and obviously on the far right of the screen is a 1 gigahertz. So that little trimmer capacitor, which is next to the final output, because the rest of it looks fairly linear, I'm just going to adjust that little trimmer cap, and there we are. Look, it sort of remedied that rather degrading response on the end. If we continue adjusting that, then we get more of a linear reading, and just a bit more adjustment, I think. Now if I just get the damn trimming tool to get in the slot, so then it dips again there, look. So back around the other way, and get a bit of a notch there, don't we? And then it lifts up again there. Now we'll just have a look at some of the biasing. I'm just keeping my eye on the current meter while we adjust the first stage bias. It's currently reading 2.8 amps at the moment, so I'm just going to see what happens there. So it's 1.3 amps, sorry, 2.6, and then as we increase the gain to around about there, it's starting to go up. So round about, we're getting a bit of a peak. I don't know if you could see it there, just right in the trace there where my finger is. We can sort of flatten that down. So just trying to get that. That's 1.6 amps. Trying to avoid peaks and troughs wherever possible. Try and get the curve as flat as we can. The trace as flat as we can, should I say. So let's just keep twiddling. So now I'm on to the second stage potentiometer, and already the current's starting to drift up rather quickly at 2.8 amps. So if we bring it down and round about there, I'd say. And then the final stage amplifier biasing, If I just adjust that. Now, for some reason on all the amplifiers, the final stage biasing doesn't really make much of a difference, apart from when you get towards the end of the potentiometer, where what it does, it then suddenly starts to climb up, does the current there, and then the response starts to go down. So, but you don't get much of a power gain, you know, like that's 1.47 amps. We're getting 4 watts. Now if I adjust the gain now, so we're getting like 1.8, that's 2 amps. We get a bit of gain at the lower end, but less gain at the top end, and then we start to get a reduced gain overall there. So let's just put it to there, I think. So I think if we now go back to the beginning again, and we just do another adjustment on the first stage again, and let's see whether, you know, we can get on the potentiometer. Always awkward, these potentiometers with the trimming tool. So again, we're getting the biasing affected there. We get very poor response. Bring the bias point back up. It starts to even out around about 2 amps roughly. About there. 1 point. Let's have a look. See what we can get out of this one. It's starting to dip again, so the peak's around about there, I'd say. Now, don't think we're going to be able to achieve any better than that, to be honest with you. I think if I let's have a look. Now we're getting, according to that, 4 watts output, so that's more than enough for what we need. That 4 watts. So if I get the marker, got the level there, and just adjust the marker, get roughly about 3.6 watts at 700 megahertz, 720 odd megahertz, 3ish, then up to about a gigahertz, 900 megahertz. We're talking 4 or 5 watts, 5.2 watts. So even more lower end, 6 watts, 7 watts. There's quite a lot of more power down below at 10-11 watts there. So I'll switch it off a moment. So that's quite a remarkable output power on that. Now obviously, as we saw the trace, where we have more power gain at the lower frequencies, and then it falls off sort of mid-band and then picks up again towards the top end in the 1 gigahertz spectrum. Another amplifier has slightly less power gain at the lower frequencies and a higher power gain in the middle, and thus then, so between all 4 amplifiers, they sort of all counteract one another, whereas one amplifier's got a deficiency in one part of the band, another amplifier's got an efficiency in that part, which then makes up for the deficiency of the other amplifier. And thus then, when all 4 amplifiers are all combined as a cumulative output, then more or less the response should be fairly linear across the band, or it should have an equal gain roughly. But I think we've done okay with that. I'll move on to the next amplifier now and see what we can do with that one. Right, we're on the second amplifier now. We've powered it up, we're running it, and it's doing quite well, although it's not as linear as the other amplifier before it. It's still quite nice. We're getting 5 watts at the top of the screen there, you can see with the marker level. We're getting considerably more power at the bottom of the band, about 15 watts, 10 to 15 watts. If I move a marker on the spectrum analyzer, keep your eye on the power level, a couple of megahertz there, down to what was it, 24 megahertz, we're getting 15 watts out of it. So it's the best I can get, I'm afraid, on this amplifier. Mid-band we're getting about, what, 5 watts, something like that, 3.8 watts roughly. And then top of the band, you know, we're fluctuating between several watts down to 5.8 at 1 gigahertz. So yeah, it's the best. I've been messing about with the bias currents and trying to get the bias set up properly. What happens is, as well, it's very easy to overdrive the amplifier. I can turn the gain up on the front of the amplifier so it does about 15 watts, this PA across all the band, but then these resistors here get intolerably hot, and they're all just nicely snug warm at the moment. They're not burning my finger ends yet. So yeah, that amplifier is definitely slightly different performance to the other three, but it's still okay. It performs quite well. It's got a very high gain, so I'm happy with it, but I'm just aware that it's got a slightly different response to the other amplifiers, and of course the biasing and everything's not making much difference to that across its linearity across the entire frequency spectrum of 1 megahertz to 1 gigahertz. So there's not much I can do to adjust it other than what I've just done by adjusting the bias and the caps. That's the best response I can get out, what we can see there on the spectrum analyzer. So I'm quite happy at this stage to close it all up now and put it back in the unit as it was and rebuild it, and then take it from there. So I wanted to show what can happen there with RF measurements, where we're measuring an amplifier that's producing at low frequency spectrum, because it's a very wide band power amplifier. We saw there in that measurement on this particular amplifier about 15 watts on the lower end of the spectrum, in the sort of sub 30 megahertz region. 15 watts output power, which has been nicely warming this 30 dB attenuator up. It got quite warm at one point because it's been running a while with it. And then at the top end, mid to top end of the radio spectrum, from around about the UHF 500 megahertz right up to 1 gigahertz, it was roughly around about 4 watts to 5 and a bit watts towards the top end. Now, because we're looking at 10 dBs per division, it means that for every graticule there's 10 dBs difference, and we could see that there was a step and then it went down, and that didn't look much on the spectrum analyzer, but that is a marked difference in RF power, obviously, because for every 3 dBs we increase RF power, we're doubling it, and likewise for every 3 dBs we attenuate RF power, we're halving it. So that one graticule difference between what was at the left of the trace and what was at the right was a marked difference in RF power, and this is why you must always choose the highest level of attenuation that you can possibly get on the input to the spectrum analyzer, because had we had looked at the overall performance of the amplifiers prior, which we were measuring, the other three of them, the average power of them was around about 4 to 5 watts, possibly 6 at the most. So if you were to choose, say for example, a 3 dB attenuator, that would half the power. So say for example we have 5 watts coming out the transmitter across the entire frequency spectrum, and we chose a 3 dB attenuator, and the RF power coming out of it will be 2.5 watts. That would be still too high for the spectrum analyzer to take. So we might, for example, choose a 6 dB or a 9 dB attenuator, and to give us a little bit of headroom, particularly with a 9 dB, because a 3 dB will reduce 5 watts to 2.5, which is still too much for this to take. Then a 6 dB will reduce it again another half. So 2.5 watts divided by 2, that will give us half again. A 9 dB would half that again as well. So then that would drop it well below the measurement limits of the spectrum analyzer, and it will give us a bit of headroom. Now obviously, even at 9 dB with that bit of headroom, with 5 watts in mind, we found there, because this is a wideband amplifier, the lower end of the frequency spectrum was doing 15 watts. 15 watts is a huge amount of RF power when you compare it against, say, 5 watts that we're expecting. So therefore that headroom is gone, and therefore you risk damaging the spectrum analyzer. So this is why you've not to overthink things. You know, sometimes you can think that an RF amplifier can be rated at 5 watts but it might be doing more power than that at other frequencies, and we've seen an example here. And so if you go choosing an attenuator that's too narrow a headroom, it would mean then that you risk overloading the spectrum analyzer and blowing it up. So a 30 dB attenuator gives a huge headroom, but obviously we're not expecting thousands of watts coming out this amplifier, or hundreds and hundreds of watts. We're expecting tens of watts maybe to come out at most, because the transistor's rating maybe up to 10 watts, 15, 20 watts, something like that. So we need to think about that when we're doing measurements. We need to look at what the amplifier can do with its supply voltage, what the rating of the transistor is that's in the circuit, and the potential for the amplifier to take off if it's overdriven. Because inputting an error on the spectrum analyzer at the RF level coming out on the track gen can have a marked difference on the output power of the amplifier. So for example, if this spectrum analyzer is capable of producing plus 20 dBm, and say for example the input to the amplifier to get 10 watts out was 0 dBm, if you accidentally type in plus 20 dBm and hit the track gen on button, this attenuator, if it was a 6 dB or a 9 dB attenuator, would be getting massive amounts of power into it if the amplifier could do that, and thus it would overload the spectrum analyzer. So when we're doing RF measurements, we always need to be aware of things that may happen that you've not yet accounted for, and that could be a higher supply voltage where an amplifier is designed to run at say 20 volts and produce 10 watts output, but say you've mistakenly thought that was 28 volts, and then it's getting extra 8 volts, so it may do a lot more power with that extra 8 volts. It may also be that you've incorrectly set the drive level to the amplifier. It could also be that we've seen here that the amplifier gives different outputs at different frequencies, and thus if that is a marked difference, then having a 6 or a 9 dB attenuator on the front of the spectrum analyzer, that little bit of headroom you had has gone, and thus the overload situation would occur on the spectrum analyzer. So it's always worth remembering, always start with the highest level of attenuation you can muster up. I mean, it doesn't matter with the spectrum analyzer, because if we put 30 dB in, some people think that might be excessive, but it gives us that massive headroom. And also, within reason, you can set the input attenuator on the spectrum analyzer so that the step attenuator in the spectrum analyzer can then make up for that 30 dB's difference to get a nice reading on the display. So you're getting that margin of error included into your measurement design, where you're using an attenuator in such a capacity where it takes into account mistakes that either happen in the measurement of the amplifier because of its performance, user error, as in the operator doing the testing as not aware of this technical specification of the amplifier and perhaps inputs the wrong levels, supply voltage differences, all kinds of manner of things. So it's always worth bearing that in mind with RF attenuators. Start with the highest level of attenuation you can that can take the power, and thus you reduce the possibility of ever damaging your spectrum analyzer. Well, I just thought while we got the thing apart before we put the amplifier module that's stood here back in the unit here, we just open up the preamplifier and have a look inside. So this socket here on the top is the input, which goes to the front panel input. We can see there we've got just zoom in a bit, we've got our friends the pi attenuator. So we've got again just here pi attenuator made of these 3 resistors, and so there we've got a tuning cap as well, another resistor going to here. We've got a top hat transistor just there, look, that's soldered down. That's the reason why the other amplifiers have a hole there. So that's a wide banded transistor. Now I'm not sure if it's biased, it may well be, it looks like it is. It's got an RFC perhaps. Is that going to the collector or the base? Let's have a look, see if there's any clues. That looks like it's going to its collector. This is like, we found this on the other Kalmus amplifier. It's like a hybrid amplifier rather than being a transistor. Most people that have worked on old PMR radios will have seen similar transistors to this used in the exciter, but being the MRF range, the Motorola MRF 237s, MRF 630s, this is like that, but it's a wide banded, sort of like a mimic device, a hybrid amplifier. So rather than it receiving biasing, it just gets the signal coming in and then volts to the collector leg, if you like, and then it produces the amplification without any biasing. But it's a high gain device that's wide banded, obviously from, you know, DC to 1 gigahertz, and so then it gets passed off, obviously, the amplified output. Interestingly enough, it looks like bridging where this transistor would go. We've got an attenuator, a pin diode, which is biased by this resistor here, and that in turn, when I move these cables out of the way, seems to route back to this leg here, which is the control leg. So we have 26 volts, 28 volts, whatever applied here, which is the high voltage, and then this connection goes to the potentiometer on the front, so we can adjust the DC voltage to that, which will then increase or decrease the gain. That'll explain why there's no series pass transistor, because we're not controlling the current to the amplifiers. We're just literally changing the biasing conditions on this pin diode there. So the supply via this resistor gets varied. The current obviously gets varied that passes through this pin diode attenuator. We've got a tuning cap on the output as well down there, which is this. It goes through a DC blocking capacitor. We've obviously got a path for the DC to ground, because obviously pin diodes, vari-caps, etc., they don't work unless they've got a DC path back to ground again. There has to be a current flow across them, particularly pin diodes. And then after the RF capacitor, we've got another resistor. Before then, we then introduce the next stage, which is this first stage amplifier. With one of these 100 ohm resistors soldered between the gate, drain source, etc. And then another tuning cap. This is flapping about a bit. I might have to do something about that, secure that, maybe put a bit of elastic on it or something, because obviously shock, that's going to break off. Then we've got, again, 2 biasing pots on this preamplifier. Next stage again. Then we're going again, same kind of design. So we've had a lot of soldering gone around here with these positioning of these capacitors to try and get optimal performance, and that's that. I'm a bit concerned about that. I'm surprised that's been allowed to just flap about in the breeze. So definitely have to stick that down with something. But yeah, so that's the 20 dB amplifier, and as you can see, it's a nice little amplifier, been well thought out. So I'd like to have a look inside the combiner next, so we'll whip the lid off that and see what's inside that. So this is what's inside that little power combiner, and have a look at it. It says it's made by is it Whirltone Incorporated, Brewster, New York. High power combiner. It says frequency 1 to 1000 megahertz, 15 watts rated. So, and that's what's in it. So it looks like as if there's some kind of ferrite beads with, what is this, rigid coax, which goes to various places inside, and little transformer things coming off with the little ferrite beads. And I wondered if it's using that coax with the 2 inner conductors. You might remember on the analysis of UHF amplifier that I did on my YouTube channel, I did an analysis of a Marconi UHF RF power amplifier, and it was this rigid coax that had 2 inner conductors that formed an RF transformer. It's manufactured like that. Some use singular coaxes and then match them in set lengths between one side of a transformer to the other using this kind of methodology. Others use this strip line that's got the 2 inner conductors in this coaxial cable, and thus it can be used as an RF transformer. So seems strange. That's the input there on one side. Let's have a look. So these are the inputs from the 4 amplifiers, and then we've got the one output there on this side. So this is the transformer element, and then we've obviously got the 4. That coaxial cable comes in underneath in that ferrite bead arrangement. This connector here goes that way, likewise this one this way, and that one that way. So a wide band. This looks like it's been getting warm because that's elastic's discoloured. So that looks like some kind of power resistor that's down there with the look of it. Not sure what that is, but looks like a resistor to me. That some kind of power resistor. Got 2 wires coming off it that are then going down, and then you've got, have we got anything on the outside of the amplifier? I don't think so. So I don't know what that's for. Some kind of, looked like it was going through the side of the amplifier, but it isn't, is it? It's strange, is that? So it's like 2 wires that are twisted around one another. Oh, look at that. It's just, obviously, that's weird, isn't it? Just flapping about. Obviously just being unravelled to get the right tuning and performance across the frequency range. It's like a select on test type thing. Bit bizarre is that. I must admit, we're expecting to see that. If anything, I expect to see a PCB inside there, copper clad PCB with a RF transformer mounted on that and all nicely soldered down, but there's a resistor down there. Looks like it's dropped off. It definitely looks like that's dropped off to me. Yes, look at that. That's another repair we've got to do. We've got to find out where that goes now. I presume it's off this PCB at the end here or somewhere like that, but that's not good, is it? It's a good job we looked in, because the resistor itself has, you know, can't grab it now. How's that come off then? It's obviously desoldered itself, I think, or something like that, or broken off. So just need to try and find out where that's come from. A 50 ohm resistor with the look of it. 5%. So I'll put that in that little box so we don't lose it. Oh. And find out where the hell that's come from. That's strange. Is that a 50 ohm as well? Then I bet it is as well. That I wouldn't be surprised. So where's that come from then? Has it come off the end of this? I bet it has. I bet it's fallen off the end of that or something. So I might have to take the whole thing out and desolder it and try and get to this. It's dropped off this end, but who knows? I'll have to look for signs of where perhaps it's been soldered prior. I think it's dropped off of this end myself. That's what I think. I think it's definitely dropped off of this end. I could be wrong, but you never know. I will find out, do further investigation. So it's a good job, isn't it? We looked at that, otherwise we would never have known. Tried to get it going again and found out that we weren't producing any output power. I don't know. We go from one crisis to another with this thing, don't we? Okay, we're back with this combiner now, having found out where that resistor went. There's a few resistors in this, both of which are on each end. So there's one on the inside and one on the outside, soldered in diagonally, different orientations to one another, and the same here. And it was this resistor at the end here that had dropped off, that got really hot and desoldered itself. It had dropped off inside because that resistor was on there. There's no resistor on the middle PCB here. So anyway, I've resoldered that back in place, and then of course just looking around inside, it is a little bit strange. I wasn't expecting it to be that kind of design. I would have expected it to have been mounted on a PCB inside, and then all this select on test sort of stuff, like this wire here, this red wire that's just doing nothing. It's just soldered to the inner of the SMA connector on the output, and it's just like a stub, a tuned stub that's obviously been bent and cut to the right length and just left inside, you know. But same here with this. I can't quite make out without getting that elastic off, but I'm just seeing if I can get focused in on it a bit better. You can see there that there's two wires which just left open-ended and twisted, and they come round. I'm not sure though if a solder to that resistor. I can't tell that. They probably are, probably one end soldered to that one end of the active part of the resistor, because the shell of the coaxial cable, the solid coaxial cable, you can see there the junction of the resistor soldered to the outer shell of the coax, and then on this side that's obviously going to the inner part of the coax, which is more than likely where that red wire solders, and then it comes round and is just left flapping about like that, you know. I mean, obviously it's elastic down. I'm not keen on that. I don't know why they designed it that way. Again, this is the other side. I've resoldered these as well. There's two resistors there, diagonals to one another on this part of the RF transformer. And obviously the way it works as well is that the active RF that comes in from the coaxial cables goes to the PCB. It's soldered then the inner onto the PCB. The outer coaxial cable of the next coax in the transformer solders to the inner, and then the inner of this coaxial cable solders to the outer of this one, and thus the power that's coming into this then goes from the inner to the outer, and the outer to the inner, and the inner to the outer, and the outer to the inner, and then it gets combined as part of a central point and then distributed out obviously to the output. And that's how the transformer works. But I have seen better examples, admittedly, you know. I mean, this isn't a particularly good example, a good design, but you can see down there where the coaxial cable has been soldered there, and that then goes to the outer of another coaxial cable, etc., and inner. Then you've got these tuned stubs like that little snake there at the bottom of the picture that comes round to a 50 ohm there, obviously gives impedance matching midway in the transformer. And then we've got the feeds then at the top of the picture to the individual RF sockets that are coming in from the amplifiers. So a very bizarre sort of thing. So midway point is where both sides got two inputs on this side going through those two lots of transformers to the middle, and then two inputs on the left side then from those two that are connecting down here. Then in the middle then we've got a feed towards the top of the picture, which is coming off on that solid coaxial cable that's elastic down on the bottom, comes through and then goes up there, look to the inner of that. And then we've got that other tuned stub, this red wire. So I wasn't expecting to see that, to be quite honest with you. It does seem a bit last minute, sort of throw it together sort of thing, but it's obviously something that they're happy with at Whirlertone, New York. But I've certainly seen better examples of RF transformers than that. But there again, this is a 1 megahertz to 1 gigahertz transformer, unlike other examples I've seen prior where the narrow band examples where a VHF transformer or UHF transformer independently, then you can get away with a lot more, whereas when you've got such a a 1 gigahertz wideband transformer is quite an achievement to some designers, so you often have to have these little tuning bits added, select on test, to try and eradicate various little problems that you might pick up on the way. I think this has been run into a high VSWR because this socket here is the output that goes to the front of the amplifier for the output, so I think there's been some imbalance, and I think the VSWR has been sky high, the power's been probably turned on, it's been producing RF output power at 10 watts or whatever, and they've just left the output unterminated, and then what's happened is then that resistor's got really hot and dropped off the board. I've checked the others, made sure the soldering's good on them, and I've resoldered them, but I think that's what's happened here, and that's obviously propagated its way back. Once that resistor's dropped off, there's been a further mismatch, which has then obviously affected the whole amplifier. You know, all these amplifiers have then failed as well, so I think that's what's happened here. Could be wrong, but I certainly suspect that. So yeah, very interesting. It's nice to look inside things, but I must admit I'm a little bit sceptical of this design on this one. Right, we've got the unit under test now with 0 dBm at 1 gigahertz, feeding 0 dBm into here at 1 gigahertz, and we've got the power adjusted to around about medium power. We're just running a sort test on it at medium power setting now for a few hours, just to make sure that it runs properly. It's been on about an hour now already, proving that level of RF has been sustained. It's keeping cool and everything, and I think we can conclude this has been successful because we weren't getting anything out to start with. Now if I alter the gain, and I'm getting quite a considerable amount of power coming out even at that, at 1 gigahertz, you know. So we're getting a fair bit of power down. It might not be 10 watts, but not far off. Sooner run it at a lower output power, about 2 watts. Just change the frequency as well, and see what that does. That's at 100 megahertz. So I'm quite happy with that, being obviously at the low medium power range, and obviously we don't want to over bias it, but we're doing pretty well there, to be honest with you. I think it's our power is not doing bad at all. So I'll leave it on for a couple more hours just to you know, a couple of watts at 1 gigahertz, just to settle it in, and put the lid on, and that's it, I think. A very strange amplifier, I must admit, and weird faults, you know, obviously with the 100 ohm resistor dropping off the circuits, and the power amplifiers, the resistor that had dropped off the board inside the power combiner as well. What else did we have? I think that's about it really. So we had the 4 amplifiers that had the below 100 ohm resistors on the output, and then the power combiner itself seemed to have a problem as well. Just seems a bit overkill to me, does this? I mean, in an enclosure that size and a narrow band amplifier, probably get a few kilowatts out of it, you know, if you're building something like this for yourself, but just to get, you know, up to 10 watts maximum between 1 megahertz to 1 gigahertz in such a large enclosure with so many amplifiers running in parallel into power combiners and splitters and preamps and everything else that's in it and all the other stuff, and you just think, you know, it's a bit OTT. Don't know what they thought of when they were building this, but it just seems a little bit overkill for what it is. I'd have expected a lot more thought going into a single amplifier that has a high output. You know, the amount of current this draws, quiescent current, even when it's not used as an RF gain, is absolutely unbelievable. It draws about 5.8 amps with no RF amplification at all. So very strange problems on it though, I must admit. I mean, it's obviously not been looked after. Who's ever had it before me, I've just left it on the you know, on the bench, and it's just been neglected, I think, which is a shame. But I'm glad being able to repair it anyway and get it going again, albeit at minimal cost, replacing 100 ohm resistors and resoldering resistors back into place that would otherwise have just dropped off. But I don't know, it seems a bit strange to me, all these problems. It's either it's not been designed very well or somebody's really neglected it. But even then, I would have thought it would have had protection against IVSWR, but it doesn't appear to have that. So if you disconnect that output and just leave it running, which I think is what's happened, the resistor in there is going to get hot, and plus as well the resistors in these amplifiers are going to get hot and drop off as well. Very, very bad design, I think, is that. But that's just my opinion, for what it's worth. It was quite an interesting little gadget, you know. We've had add it to bits, hell of a job to strip it down and take it all apart, and I think we've done really well considering. Anyway, it's working, we're getting power coming out of it, and it's got a 40 dB gain, so can't grumble at that, because that's what it's advertised as a 40 dB power amplifier. So we'll leave it running for another couple of hours and make sure that the output remains continuous at this 1 GHz frequency that we're testing it at. But with that, I think that's the end of the video. I hope you've enjoyed it. I certainly have. As I say, it's not about the destination, it's more about the journey, and the fact that we've learned about it and stripped it down and then looked at all the circuit design and gone the right way through it, methodically swept it as well on the spectrum analyzer, track gen, and we've aligned each amplifier after doing a repair on each amplifier. We've then reassembled it, tested it, we've then done a repair on the power combiner, and believe it or not, that's actually getting warm as I'm talking to you and I'm touching that. There's some heat there, so quite interesting. So yeah, those resistors obviously getting warm. So yeah, very interesting. So I think with that, I'll end the video here. If you like the video, please subscribe, give it a thumbs up as well, and by all means put your comments in below, and I will catch you in the next video. Thank you very much for watching, and catch you again. Bye for now. Bye bye.